Hey there, sleepy explorers. Welcome to the Sleepy Professor. I'm so glad you're here with me tonight, ready to embark on a peaceful journey through one of the most profound mysteries we could ever ponder, the origin of our universe. Settle in, get comfortable, and let the calm of the night wash over you. Let your thoughts drift as we explore the incredible, awe-inspiring story of how everything came to be. You've probably heard the term Big Bang thrown around before, but have you ever stopped to truly wonder what it means? How can we even begin to comprehend something so vast, so mind-boggling, so distant? Well, tonight, we're going to unravel this mystery together, step by soothing step. We'll break it down in a way that feels natural and easy to follow, all while keeping the tone gentle and calming. Think of the universe as an endless, mysterious ocean, stretching far beyond what we can imagine. There's so much out there yet to be discovered, so many wonders that remain hidden, waiting for us to understand. But the Big Bang, this is where it all starts. Every star, every planet, every galaxy, and yes, even us, everything is tied back to that one ancient event. And it all begins in a place that's hard to even picture, with nothing, a single point, impossibly dense, impossibly small, containing everything that would ever exist. All the stars, all the galaxies, all the time and space, all crammed into something smaller than a pinprick. It sounds like a dream, right? Nothing, but everything, in one tiny, unimaginable spot. It's a concept that's almost impossible to grasp. How can something so vast come from so little? But that's the beauty of the Big Bang theory. It explains how, from that nothingness, everything we know today, the stars, the planets, even life itself came into existence. Before the Big Bang, there was no before in the way we understand time. Time itself didn't even exist. So, as we journey through this topic tonight, let's leave behind our usual concepts of time and space. Instead, let's open ourselves to a new way of thinking, a way that invites us to step back, breathe deeply, and simply marvel at the unimaginable complexity of it all. We're not just talking about ancient history here. This is an ongoing story. The universe is still expanding, and so are we in our understanding of how it all fits together, from the Big Bang to the present day, to the quiet, gentle unfolding of the cosmos right now. We're all part of this incredible journey. So, as we begin this sleepy voyage through the universe, let yourself relax, let yourself drift with the flow of time and space, knowing that you are connected to this grand, endless story. Right now, we'll start at the very beginning, the moment when time and space themselves were born, and the universe began to unfold in ways that continue to amaze and inspire us all. And remember, in this vast cosmos, you're not just a spectator, you're part of the story, and that's something truly extraordinary. What was there before the Big Bang? Now, let's gently slide into the idea of what was there before the Big Bang, or, more accurately, what we think or don't think was there. Take a deep breath as we explore this together. The Big Bang Theory doesn't just explain how the universe began, it also challenges our very understanding of time. See, the concept of before doesn't really apply. It's hard to imagine, I know. We live in a world where everything happens in sequence, one moment after the next. But time itself didn't exist in the way we understand it before the Big Bang. Imagine for a moment trying to describe color to someone who has never seen. That's what it's like when we try to grasp time before time existed. In fact, the moment of the Big Bang can be thought of as the beginning of time itself. It's almost as if time, space, and the very fabric of reality were all born in that instant. Everything you've ever experienced, every second that has ticked by, every moment of your life, all of it traces back to that singular point. This means that asking what came before the Big Bang is a little like asking what's north of the North Pole. It's a question that doesn't quite make sense when you really think about it. Time as we know it simply didn't exist. The Big Bang is in many ways the point where time began. Before that moment, there was no before. There was no clock ticking, no sequence of events, no cause and effect, just nothing. Or perhaps everything compressed into a point of infinite potential. But that doesn't stop us from trying to understand what might have come before, does it? The human mind is curious, always reaching, always wondering. Some scientists wonder if our universe is just one of many, part of a multiverse, where different universes are constantly being born, dying, and recreating themselves. This idea is fascinating, an endless cycle of births and rebirths, stretching across infinite dimensions. Imagine that infinite number of universes, each one with its own beginning, expansion, and end, each one with its own laws of physics, its own constants, its own story unfolding. Some might be similar to ours, with stars and planets, and perhaps even life. Others might be utterly alien, with forms of matter and energy we can't even conceive of. It's mind-blowing, but it's a theory that's gaining some traction among physicists and cosmologists. In some versions of the multiverse theory, these universes exist like bubbles in an infinite ocean, each one separate, each one complete. They might never interact with each other, forever isolated by the boundaries of their own space-time. Or perhaps they do interact in ways we haven't yet discovered, creating ripples and echoes that we might one day detect. Another possibility is that our universe has no beginning at all, that it has always existed in some form, just constantly changing and evolving. This is a harder concept to grasp because our everyday experience tells us that everything has a beginning and an end. But perhaps on the cosmic scale, the rules are different. Perhaps the universe is eternal, cycling through endless transformations. Some theories propose that our universe could have emerged from a big bounce, a kind of cosmic rebound after a previous universe collapsed. This idea suggests that the Big Bang wasn't the absolute beginning, but rather a transition point in an ongoing cycle of universes. Picture a cosmic heartbeat, expanding and contracting forever. Each contraction might create conditions for a new expansion, a new Big Bang, a new universe with new possibilities. This cyclic model is appealing in some ways because it removes the thorny question of ultimate origins. Instead of asking where did everything come from, we simply accept that it has always been here, in one form or another, endlessly recycling itself. It's like the water cycle on Earth, but on a cosmic scale. Water evaporates, forms clouds, falls as rain, flows to the ocean, and evaporates again. Perhaps the universe works the same way, just on an unimaginably larger scale. But, for tonight, let's not get too caught up in what might have happened before the Big Bang. It's a mystery we may never fully solve. Instead, let's focus on the story that we do know, the story of how everything we can see, touch, and feel emerged from that single extraordinary moment, the Big Bang, the birth of everything we know, deepening our understanding, the nature of time and existence. As we gently move forward, we can't help but wonder what was there before the Big Bang. We've talked about how time itself didn't exist in the way we understand it before that moment. But what about the universe? Was there a before at all, or is that question simply beyond the limits of our comprehension? You see, we humans are naturally inclined to think of time as a line, one event following another, one moment after the next, a steady flow of existence. It's how we experience life. You wake up in the morning, the day progresses, evening comes, you sleep, and then the cycle begins again. This linear experience of time is so fundamental to how we perceive reality that it's almost impossible to imagine it any other way. But when we approach the Big Bang, we're forced to let go of that familiar linear concept. The Big Bang wasn't just the beginning of everything in the universe. It was the very beginning of time and space itself. Everything that makes up the universe, including the fabric of time, space, and even the laws of physics, emerged from that singular moment. It's like the universe wrote its own rulebook in that instant, establishing the principles by which everything would operate. When we try to imagine what could have been before the Big Bang, we're left grappling with a paradox. If there was no time, then how could anything have happened before it? Events require time in which to occur. Change requires a before and an after. But if there's no time, there can be no sequence, no change, no events. That question leads us into some fascinating and mysterious theories, and even though we don't have all the answers, let's explore some of these ideas to understand the possibilities. Let your mind relax as we venture into these abstract concepts. There's no pressure to understand everything completely. Just let the ideas wash over you like gentle waves, each one revealing a little more about the mysterious nature of existence. The limits of our understanding time and space. To help grasp this, imagine a balloon that's being inflated. As the balloon expands, everything on the surface of the balloon moves further apart. If you were a tiny dot on that balloon, you would feel the surface stretching out from you in every direction. Everything would be moving away from you, not because you're special or at the center, but because the surface itself is expanding. Now, think of the Big Bang as the moment when the balloon started inflating, but this balloon is the entire universe, including time and space. As space expands, time itself starts moving forward. The fabric of the balloon represents the fabric of space-time, that mysterious weaving together of space and time that Einstein showed us. Before the Big Bang, there was no outside of space and time. We often picture the universe as a container, something sitting inside a larger space. But the truth is, there was no container, no outside, and no edges. Everything, time, space, matter, was confined to that incredibly small point. So, when we ask, what happened before the Big Bang? It's like asking what lies to the north of the North Pole. The very concept of before is simply not applicable. At the North Pole, every direction is south. There is no north beyond it. Similarly, before the Big Bang, there was no before. The question itself becomes meaningless, not because we lack knowledge, but because the concept doesn't apply in that context. It's a profound realization that challenges our everyday intuitions about cause and effect, about beginnings and endings. The concept of a beginning becomes even more intriguing when we consider the nature of space and time. According to Einstein's theory of general relativity, time and space are linked. They form what we call space-time, and space-time itself is something that can stretch and warp. When you stretch space, you stretch time too. Near a massive object like a black hole, time actually moves more slowly than it does in empty space. This isn't just theory, it's been measured and confirmed. So, to say that the Big Bang began both time and space is to say that time itself had a starting point. There was no time before the Big Bang, just as there was no space. It's a concept so strange and counterintuitive that it can be hard to grasp, but it's the foundation of the Big Bang theory. And as strange as it seems, all the evidence we have supports this idea. The universe really did have a beginning, and that beginning included the beginning of time itself. The multiverse theory. A universe among many. Even though the question of what was before the Big Bang is difficult to answer, some ideas stretch our imaginations even further. One such idea is the multiverse theory, which proposes that our universe is just one of many. According to this theory, there could be an infinite number of universes, all separate but existing in parallel. Each of these universes would have its own Big Bang, its own set of laws, and potentially even its own form of time. In the multiverse model, our universe could have emerged from a bubble in an ever-expanding sea of other universes. These universes might be connected in ways we cannot yet comprehend, but the basic premise is that there could be many Big Bangs happening at different times, in different locations beyond the reach of our perception. Each universe would have its own unique characteristics, different fundamental forces, different particle types, different physical laws. Some of these universes might be similar to ours, with stars and planets and perhaps even life. Others might be radically different, with entirely alien forms of matter and energy. In some universes, gravity might be stronger, causing all matter to collapse into black holes almost immediately. In others, gravity might be so weak that galaxies could never form. Some might have more dimensions than our 3 spatial dimensions and 1 time dimension. The possibilities are truly endless. The idea of the multiverse is both exciting and humbling because it suggests that our universe may not be as unique as we once thought. For centuries, humans thought Earth was the center of everything. Then we learned that Earth orbits the Sun. Then we discovered that the Sun is just one star among billions in our galaxy. Then we found out that our galaxy is one of billions in the universe. And now the multiverse theory suggests that even our universe might be just one among countless others. It's hard to picture, but it's a possibility that scientists continue to explore with both hope and caution. After all, if there are an infinite number of universes, who's to say what kinds of incredible structures and life forms might exist in other worlds? Perhaps there are universes where the fundamental constants are tuned differently, allowing for forms of complexity and consciousness we can't even imagine. Some versions of the multiverse theory suggest that every quantum possibility creates a new universe, branching off from our own. Every time a particle could go left or right, the universe splits, and both possibilities are realized in different universes. This many worlds interpretation is mind-bending, suggesting that there are versions of you in countless other universes, each one having made slightly different choices, experiencing slightly different lives. The cyclic model, rebirth through collapse. But what if our universe is just one part of an endless cycle, rather than something born out of nothing? Another fascinating idea is the cyclic model. This theory suggests that the universe goes through infinite cycles of birth, death, and rebirth. According to this model, the Big Bang wasn't the first beginning, nor will it be the last. Instead, the universe might collapse in on itself, only to explode again, creating a new cycle of expansion. This idea is often called the Big Bounce theory. The concept is that after the universe reaches a point where its expansion slows down and reverses due to the gravitational pull of all the matter in the universe will collapse, eventually reaching a point of singularity once again. And from this state, a new Big Bang could occur, starting the process over again. Imagine the universe as breathing, expanding as it inhales, contracting as it exhales, over and over again across eternity. Each breath would be billions of years long, but from the perspective of the cosmos, it might be as natural and rhythmic as your own breathing right now. In and out, expansion and contraction, creation and destruction, all part of one vast cosmic cycle. The cyclic model has been around for a long time, with various scientists proposing slightly different versions. One popular version, proposed by physicist Roger Penrose, suggests that each cycle is slightly different, with the new universe growing out of the remnants of the old one. This idea provides a kind of cosmic recycling system, an infinite loop where the universe is constantly being reborn and expanding again and again. In Penrose's model, information from the previous universe might even carry over into the next one, encoded in subtle patterns in the cosmic microwave background. If this is true, we might be able to detect echoes of universes that came before ours, glimpses of cosmic history that extends back far beyond our own Big Bang. While this model is captivating, it still faces many challenges. For example, we don't yet have conclusive evidence that the universe is contracting before expanding, and there are many unanswered questions about the mechanics of such a cycle. What triggers the bounce? What prevents the universe from collapsing all the way to a singularity? How does information survive the transition from one cycle to the next? But it's an idea that remains on the table, offering an alternative view of the universe's beginnings. No beginning, the steady-state model. Finally, there's another idea worth mentioning. The steady-state model, unlike the Big Bang theory, which suggests that the universe had a specific beginning, the steady-state model proposes that the universe has always existed in roughly the same state. According to this theory, new matter is continuously created to fill the space as the universe expands, so the overall density remains the same, even though it's getting bigger. This model was appealing to some scientists because it avoided the thorny philosophical question of ultimate origins. If the universe has always existed and will always exist, then we don't need to ask where it came from or what caused it to begin. It's simply always been here, eternally creating and expanding. While this theory was popular in the early 20th century, it has since been largely replaced by the Big Bang theory, especially after the discovery of the cosmic microwave background radiation. The CMB is strong evidence for the Big Bang, showing that the universe was once much hotter and denser than it is now. This discovery dealt a serious blow to the steady-state model, and most scientists now accept the Big Bang theory. However, some scientists still ponder its implications, particularly in trying to understand the universe's long-term behavior. Could there be elements of truth in the steady-state model, even if it's not the complete picture? Might some form of matter creation be happening even now, in ways we haven't yet detected? These questions keep cosmologists curious and searching for answers, letting go of the before. So, as we move forward in our exploration, it's important to remember that trying to grasp what happened before the Big Bang may not be the right question. The true marvel of the Big Bang theory isn't necessarily about finding answers to our questions of the past, but rather understanding how everything came to be from a point of nothingness. It forces us to think beyond our ordinary concepts of time, space, and matter, and to embrace the infinite mystery that surrounds us. The question itself might be like asking, what does blue sound like? It's mixing categories that don't quite fit together. Time is a property of our universe, and asking what happened before time began might simply be asking a question that has no meaningful answer. As we continue this journey through the cosmos, remember that we are all part of this incredible unfolding story, one that began in a way we can barely comprehend, but just because we don't have all the answers doesn't mean we aren't on the right track. After all, the universe itself is full of mysteries that may never fully reveal themselves to us, and yet we're still here, trying to understand, seeking knowledge, reaching out with our minds to touch the very edges of existence. And perhaps that reaching, that questioning, that wonder is itself part of what makes us human. We are the universe's way of knowing itself, conscious beings made of stardust, pondering our own origins and the nature of reality. It's a beautiful paradox, and one worth contemplating as we continue our journey. The Big Bang event, the moment everything changed. Now that we've gently settled into the ideas surrounding what came before the Big Bang, or the possibility that there was no before, it's time to talk about the event itself. Take another deep breath. Let your body relax. We're about to explore the most extraordinary moment in all of existence. The Big Bang wasn't an explosion, like the name might suggest. Instead, it was the rapid expansion of space itself. Imagine space stretching outward from a single infinitely dense point. No fire, no sound. Just an incredible peaceful unfolding of the universe, growing from a singularity into everything we see today. It's hard to picture, I know. We often imagine the beginning of the universe as a loud, chaotic explosion, like fireworks or a supernova. But the truth is, the Big Bang was a delicate expansion, almost as if the universe was gently stretching, like a rubber band being slowly pulled apart. The difference is, This expansion wasn't just the spread of matter, it was the very stretching of space-time. Space itself was growing, stretching, and unfolding. Every part of the universe, everything from galaxies to atoms, was being pulled apart as the universe expanded. At the moment of the Big Bang, everything that we know, every star, every planet, every tiny particle was compressed into an incredibly small, hot, and dense state. This point, called a singularity, was so tiny and dense that it defies our usual understanding of physics. It wasn't just a small dot, it was a place where the laws of physics as we know them didn't apply. Everything was contained in an infinitely small space. It's like imagining that the entire universe was packed into something smaller than a speck of dust, yet somehow it contained everything that would ever exist. All the matter, all the energy, all the potential for everything that would ever be, compressed into a point of infinite density. And then, in an instant that we can't fully comprehend, it began to expand. Cosmic inflation, the first fraction of a second. Now, this is where things get a bit more interesting and mind-bending. The Big Bang didn't just happen slowly over time. It started with a period of incredibly rapid expansion, known as cosmic inflation. This rapid growth happened in the first fraction of a second, faster than the speed of light. In that short moment, the universe grew exponentially, from smaller than an atom to about the size of a melon. Can you imagine that? In less than a blink of an eye, space itself was stretching so quickly that it covered a vast amount of distance. To put it in perspective, imagine if you could take a grain of sand in a fraction of a second, expand it to the size of our entire observable universe. That's roughly the scale of cosmic inflation we're talking about. It's so fast, so dramatic, that it almost seems impossible, and yet, the evidence suggests this is exactly what happened. Cosmic inflation is an idea proposed by physicist Alan Guth in the 1980s, and it helped solve some big puzzles about the early universe. For example, the universe was remarkably smooth and uniform, yet the Big Bang itself suggests it should have been very chaotic and uneven. How did everything become so evenly distributed? Inflation explains how such smoothness could have emerged from such a turbulent start. During inflation, tiny quantum fluctuations in the universe's energy field stretched out, creating the seed of the structure that we see today: galaxies, clusters, and vast voids. Those early fluctuations stretched across the universe became the uneven distribution of matter we observe in the cosmic web today. Every galaxy, every cluster, every vast empty region can trace its origins back to quantum fluctuations that were magnified during that first fraction of a second. It's remarkable when you think about it. The largest structures in the universe, vast superclusters of galaxies spanning hundreds of millions of light-years, began as quantum fluctuations smaller than an atom. It's like the entire cosmic architecture was written in quantum code, then blown up to cosmic proportions by inflation. The temperature and density. A hot, chaotic soup. Now let's imagine what the universe looked like in those early moments. It was so hot that even light couldn't escape. The temperature was billions of degrees, far hotter than the core of any star that exists today. It was filled with a dense soup of particles, energy, and radiation. This was a time before atoms existed. Instead, there were just subatomic particles, like protons, neutrons, and electrons, all zipping around at incredible speeds. The energy was so intense that particles were constantly being created and destroyed. Matter and antimatter would collide and annihilate each other, producing pure energy, which would then condense back into particles. It was a roiling chaos of energy and matter, transforming back and forth, unable to settle into any stable form. As the universe expanded and cooled, these particles began to slow down and combine to form atoms. But it didn't happen right away. The universe stayed too hot for atoms to form for the first few minutes. At this point, the universe was still in a phase where everything was interacting with one another, in the most chaotic, intense way possible. Imagine trying to form a snowflake in a boiling pot of water. That's kind of what the universe was like, too hot for anything to stay together long enough to form anything stable. The photons, particles of light, were constantly interacting with the free electrons, scattering off them in a cosmic game of pinball. This made the universe opaque, a glowing fog of energy and matter, where light couldn't travel more than a tiny distance before being absorbed or scattered. The first few minutes, creation of the first elements. As the universe cooled further, something extraordinary happened. After a few minutes, the first elements began to form: hydrogen, helium, and a tiny bit of lithium. These are the first elements of matter in the universe. It's incredible to think that every atom in your body, in the air you breathe, and in the stars themselves, can trace its origins to these first moments of creation. They're all descendants of the Big Bang. This process of element creation is called nucleosynthesis. In the first few minutes, the universe was cooling just enough for nuclear reactions to take place, and these reactions produced the most basic elements we know today. But hydrogen was by far the most abundant element, making up about 75% of the universe's normal matter. Helium followed behind with about 25%, and the other elements, like lithium, were present only in trace amounts. This ratio, this precise proportion of hydrogen to helium, is one of the strongest pieces of evidence for the Big Bang theory. Scientists can predict exactly what ratio should have formed based on the conditions in the early universe, and when we measure the actual amounts of hydrogen and helium in the cosmos, they match the predictions almost perfectly. It's a beautiful confirmation of our understanding. The fact that we can explain the abundance of elements in the universe, that we can trace them back to specific nuclear reactions in the first few minutes after the Big Bang, is one of the triumphs of modern cosmology. It connects the distant past to the present moment, showing us that we truly understand something fundamental about how the universe works. The universe's first light, releasing the radiation. After about 380,000 years, the universe had cooled enough for atoms to form. This marked the next major step in the evolution of the universe, the formation of neutral atoms. As electrons finally paired up with protons and neutrons, light could now travel freely through space. Before this point, the universe was opaque, filled with a glowing, dense fog of particles. But as neutral atoms formed, this fog cleared and light was able to travel across the universe for the first time. This was the birth of the first light, and it left behind a faint glow, which we can still detect today. This glow is known as the cosmic microwave background, the CMB, and it provides a snapshot of the universe when it was just 380,000 years old. This faint light, scattered across the sky, is like the leftover heat from the Big Bang itself. Scientists can study the CMB to learn about the early universe, helping us understand how the universe grew and evolved over time. The CMB is an incredibly important clue in understanding the Big Bang. It's not just a leftover glow from the past. It's a direct link to the moment when the universe became transparent and light was able to travel freely. Today, the CMB is still detectable in all directions, and studying it gives us invaluable insight into the state of the universe when it was still very young. In fact, the CMB is so uniform across the sky that it tells us the early universe was remarkably homogeneous. But it also has tiny variations, tiny temperature fluctuations of just a few millionths of a degree. These tiny variations are the seeds of all structure in the universe, the regions that would eventually collapse to form galaxies and stars. The birth of matter and energy. A new era begins. After this first light, the universe continued to cool and evolve. The next chapter in the universe's story was the formation of galaxies and stars. But this would take hundreds of millions of years. For now, the universe was still a vast sea of hydrogen and helium, and gravity began pulling this matter together. Slowly, the seeds of the galaxies were sown. And so, the universe, which had begun from that singularity, an infinitesimally small point, was beginning to take shape. The building blocks of stars and galaxies were being set into motion. The light that we see today, the stars we gaze at from our homes, and the very atoms that make up our bodies, all have their origins in the very beginning, in the first few moments after the Big Bang. Everything you've ever touched, everything you've ever seen, everything you are, was born in those first moments. You are made of atoms that were forged in the heart of the Big Bang and in the cores of stars. You are, quite literally, stardust, a temporary collection of ancient matter that has been recycling through the cosmos for billions of years. The expanding universe, still growing. One of the most mind-blowing aspects of the Big Bang is that the universe is still expanding. The galaxies that we see today are all moving away from each other, carried apart by the stretching of space itself. This expanding universe is not just a thing of the past. It's an ongoing process. The universe is getting bigger every moment, stretching out into the unknown, and this expansion is accelerating, meaning it's getting faster over time. So, while the Big Bang may have occurred 13.8 billion years ago, the expansion of the universe is still happening today, and who knows what the universe will look like in the future? Will it keep expanding forever, or will it eventually slow down and collapse back in on itself? These are questions scientists are still grappling with, but the journey of the universe from the first instant to the present moment is an unfolding story that continues to captivate and inspire. In 1998, astronomers made a startling discovery by studying distant supernovae. They found that the expansion of the universe isn't just continuing, it's speeding up. This was completely unexpected. Something is pushing the universe apart, some mysterious force that we've named dark energy. We don't know what it is, but it makes up about 68% of the total energy in the universe. This means that the fate of the universe might be an endless expansion, with galaxies moving further and further apart until, in the unimaginably distant future, each galaxy becomes isolated, alone in an ever-expanding void. It's a somewhat melancholy vision, but it's what the evidence currently suggests. The early universe, hot and dense. We've already travelled through the moment of the Big Bang itself, the rapid expansion, and the creation of the first elements. But what happened next? What did the universe look like in those early years, as it cooled down and began to form the basic building blocks of everything we know today? The first few 100,000 years after the Big Bang were a time of incredible transformation. The universe was a chaotic and hostile place, filled with high-energy radiation and particles flying around at unimaginable speeds. But as it cooled, the universe began to calm, and the seeds of stars, galaxies, and even life began to take shape. Let your mind drift as we explore this era. There's a peaceful rhythm to the cooling of the universe, a gradual settling that mirrors the way you might feel yourself relaxing right now. The universe becomes transparent. In the very beginning, the universe was so hot that no stable atoms could form. It was filled with a soup of particles, protons, neutrons, electrons, and light, constantly colliding with each other, preventing light from traveling freely through space. This made the universe opaque, like a dense fog where no light could escape. The photons, trying to travel through space, would immediately bump into free electrons, scatter in a new direction, bump into another electron, and scatter again. It was like trying to walk through a crowded room where everyone is moving randomly. You can't get very far before bumping into someone. But after about 380,000 years, the universe began to cool enough for electrons to combine with protons and neutrons to form neutral atoms, mostly hydrogen and helium. With this, something incredible happened. The universe for the first time became transparent. Light could finally travel freely, and the universe was no longer a chaotic soup of particles. This transition marked the beginning of a new era, one where light could travel across the universe. It also created the cosmic microwave background radiation we talked about earlier, which still exists today, faintly illuminating the entire universe. This faint glow is like a photograph of the universe when it was just 380,000 years old, and studying it allows scientists to look back in time, getting a glimpse of what the universe was like in its earliest stages. The moment of recombination, when electrons and protons came together to form atoms, was like the universe opening its eyes for the first time. Suddenly, it could see, light could travel, information could cross vast distances. The fog had lifted. The first atoms' birth of matter. The cooling of the universe wasn't just a matter of light being able to travel. It was also a critical moment in the formation of matter. Before the universe cooled enough, particles were so energetic that they couldn't bind together to form stable atoms. But as things began to cool, the energy dropped enough to allow protons and electrons to form the first hydrogen atoms. These early atoms were mostly hydrogen, the simplest and most abundant element in the universe, along with small amounts of helium. It's amazing to think that the very first atoms were created at this moment, and that everything that came after, from stars to planets to life itself, was built on these first simple elements. This marked the beginning of a chain reaction that would lead to the formation of stars, galaxies, and eventually life. Hydrogen, with its single proton and single electron, is the simplest atom possible. And yet from this simplicity would come all the complexity of the universe. Stars would form from hydrogen. Inside those stars, hydrogen would fuse into helium, then helium into carbon, and so on up the periodic table. Eventually, these heavier elements would be scattered through space when stars died, seeding the formation of new stars and planets. The formation of hydrogen and helium. Hydrogen atoms, which were the building blocks of everything, made up about 75% of the mass of the universe. Helium came next, forming from the fusion of protons and neutrons in a process that occurred during the first few minutes of the Big Bang. These two elements, hydrogen and helium, would go on to be the primary materials that stars and galaxies would form from. In fact, nearly all the elements that make up everything we see today, planets, stars, even our own bodies, came from the basic hydrogen and helium atoms that first emerged from the Big Bang. The heavier elements like carbon, oxygen, and iron were only created later, inside stars themselves, when they began to burn through their fuel. This is a profound realization. The atoms in your body weren't all created at the same time. The hydrogen in your water molecules, in the proteins that make up your cells, that hydrogen is primordial. It dates back to the first few minutes after the Big Bang. But the carbon in your DNA, the calcium in your bones, the iron in your blood, those atoms were created billions of years later, inside stars that lived and died before our solar system even formed. But at this point, the universe was still filled almost entirely with hydrogen, with only small traces of helium. For millions of years, this hydrogen gas drifted freely through space, slowly collecting under the influence of gravity, beginning the slow process that would lead to the formation of the first stars and galaxies. The cosmic dark ages. Before the first stars could shine, the universe entered a period known as the cosmic dark ages. During this time, the universe was mostly empty space, filled with hydrogen and helium gas. There were no stars, no galaxies, just an endless void waiting to be filled. This was the time when the universe was dark. There were no lights in the sky except for the faint glow of the cosmic microwave background. The universe was still very young, and everything was still in its infancy. It was during this time that gravity started to work its magic, slowly pulling matter together into clumps. Although the universe was mostly dark, this period was anything but empty. Tiny ripples in the distribution of matter, the ones that were stretched out during cosmic inflation, started to grow. Over millions of years, these ripples became denser and denser, eventually collapsing under their own gravity to form the first stars. It's a patient process. This cosmic evolution, nothing happens quickly on the universal scale. Millions of years pass like moments in the grand scheme of things. Gravity works slowly but inexorably, drawing matter together, building structure out of chaos. The birth of the first stars. After about 200 to 400 million years, the universe had cooled enough for gravity to pull hydrogen gas together and form the first stars. These stars were massive, much larger than most of the stars we see today. They burned very hot and burned through their fuel quickly, living only a few million years before they exploded in spectacular supernovae. These supernovae created heavier elements, such as oxygen, carbon, and iron, which were then scattered throughout the universe. The birth of stars also marked the birth of galaxies. Stars began to clump together into galaxies, vast collections of stars, gas, and dust, held together by gravity. These early galaxies were small and irregular, but over time they grew larger and began to form the familiar spiral and elliptical shapes we see today. The first stars weren't just important because they lit up the universe for the first time. They were also responsible for creating the building blocks of life. The elements produced in these early stars would eventually form planets, and on those planets, life would have the chance to emerge. So in a very real sense, you and I are made of stardust, elements that were formed in the hearts of the very first stars. These first stars were like cosmic alchemists, transforming simple hydrogen and helium into the rich palette of elements that would paint the universe. Every breath you take, every thought you think, is enabled by atoms that were forged in the nuclear furnaces of ancient stars. It's a beautiful connection across time and space. The formation of galaxies. As the first stars began to form, they didn't just exist in isolation. They clumped together under the influence of gravity, forming the first galaxies. A galaxy is a massive collection of stars, gas, and dust, all bound together by gravity. In the early universe, galaxies were small and irregular in shape, but over billions of years, they would evolve into the vast, complex structures we see today. These early galaxies were crucial to the evolution of the universe. The stars within them began to form heavier elements, like carbon and oxygen, which were essential for the creation of planets and life. These elements were scattered throughout the universe when the stars died and exploded, creating new generations of stars and planets. It was a process of constant recycling, with each generation of stars creating the ingredients for the next. Galaxies are like cities of stars, vast communities where stellar generations are born, live, and die. They're held together by gravity, spinning through space in majestic spirals or clustered in great elliptical formations. And at the center of most galaxies lurks something mysterious and powerful: the role of dark matter. During the time that the first stars and galaxies were forming, another mysterious substance was playing a key role: dark matter. Dark matter is a form of matter that doesn't interact with light, so we can't see it directly. However, we know it's there because of its gravitational effects on galaxies and clusters of galaxies. Dark matter acted as a kind of scaffolding for the universe. It helped to pull matter together, creating the first stars and galaxies. Without dark matter, the formation of galaxies would have been much slower, if not impossible. Even though we can't see dark matter, we know it makes up about 27% of the universe's total mass, and its influence is felt everywhere in the cosmos. Imagine trying to build a house without a frame. The walls would have nothing to attach to, no structure to support them. Dark matter is like that invisible frame, holding the universe together, guiding the formation of structure, even though we can't see it directly. We only know it's there by watching how visible matter behaves, how galaxies spin, how light bends around massive clusters. The first lights in the universe. As the first stars began to shine, the universe was finally illuminated for the first time. These stars burned with intense heat and light, casting their glow across the universe. They were the first beacons in an otherwise dark universe. They didn't last long. These massive stars burned through their fuel quickly and exploded in supernovae, but in their brief lives, they created the elements needed for the next generations of stars and planets. In a sense, these first lights were the beginning of everything we know. They created the elements that would later form planets, and their light illuminated the universe, helping it evolve from a dark, empty place to the rich, dynamic universe we see today. The darkness that had reigned for hundreds of millions of years was finally broken, and the universe began to shine. The formation of atoms and the first light, a deeper exploration. After the Big Bang and the intense early moments of rapid expansion and cooling, the universe began to settle into a more calm state, but it was still a long way from the calm, star-filled sky we see today. The next phase in the evolution of the universe was one of great importance, marking the transition from a hot, dense, glowing soup of particles to the formation of neutral atoms and the first light that would travel freely through space. This moment set the stage for everything that came after. Let's take our time with this chapter. There's no rush. Like the universe itself, we can unfold slowly and gently. The universe cools enough for atoms to form. Around 380,000 years after the Big Bang, the universe had cooled to a point where protons, neutrons, and electrons could combine to form neutral atoms. This was a crucial moment in the history of the universe. Until now, everything had been in a highly energetic state, with particles zipping around at incredible speeds, not forming any stable matter. The temperature was so high that even atoms couldn't hold together. But as the universe continued to expand and cool, the energy began to dissipate. The temperature dropped to a level where particles began to slow down, and this gave protons, the positively charged particles, the chance to bond with electrons, the negatively charged ones, forming the first hydrogen atoms. Some of the heavier elements, such as helium, began to form as well, though in much smaller quantities. For the first time in the history of the universe, matter began to take on a stable, recognizable form. These hydrogen atoms, which would go on to be the building blocks for all future stars, galaxies, and planets, were the most abundant form of matter in the universe at this stage. Together with helium, they made up almost all the visible matter that would eventually come together to form stars and galaxies. This process didn't happen everywhere at once. Different regions of the universe cooled at slightly different rates, creating subtle variations in when atoms formed. These variations would have lasting consequences, becoming the seeds of future structure in the cosmos. The era of recombination. A universe becomes transparent. The process of atom formation is known as recombination, a time when the universe became transparent for the first time. Before this, the universe had been so hot and dense that light couldn't travel freely. The universe was essentially opaque. Light was constantly being scattered by free electrons, creating a fog of radiation that blocked our view of anything beyond. But as the temperature of the universe dropped below 3000 Kelvin, atoms began to form, and this allowed light to travel through space for the first time. It was like a fog clearing after a long storm. Suddenly, the universe was transparent. This allowed photons, particles of light, to travel freely, creating what we call the cosmic microwave background radiation. The CMB is like a snapshot of the universe when it was just 380,000 years old, and it provides us with crucial information about the early stages of the universe. By studying the CMB, scientists can understand the conditions of the universe at that time and learn about the forces that shaped its evolution. This faint glow, coming from all directions, is still present in the universe today, a leftover echo of the Big Bang. When scientists first discovered the CMB in 1964, it was by accident. Two radio astronomers, Arno Penzias and Robert Wilson, were trying to eliminate a persistent background noise from their antenna. They cleaned out bird droppings, checked every component, but the noise remained. Eventually, they realized they had discovered something extraordinary, the afterglow of creation itself. The first light. What did the universe look like? So, what did the universe look like once it became transparent? For starters, it was a very different place from what we see now. The universe was still filled with hydrogen and helium atoms, and light could now travel freely, but there were no stars, no galaxies, just this vast, empty expanse of matter and radiation. It was a dimly lit place, with the first light stretching out in every direction, but no sources of light like the stars we see today. During this time, the universe was in a state known as the cosmic dark ages. Even though light could now travel, there were no stars yet to light up the sky. For millions of years, the universe was a quiet, still place, with only the faint glow of the CMB breaking the darkness. The next major step in the universe's evolution would be the formation of the first stars, which would begin to illuminate the cosmos and transform it from a dark, empty void into a place filled with light, warmth, and activity. Imagine floating in this early universe. You would see a faint, uniform glow in every direction, the color of the CMB, but it wouldn't be the microwave radiation we detect today. Back then, it would have been visible light, a dull red glow like the embers of a dying fire. And beyond that, nothing but darkness and the whisper of hydrogen atoms drifting through space. The formation of the first stars lighting the universe. After millions of years of darkness, gravity began to work its magic. Tiny fluctuations in the density of matter in the early universe, set in motion during the period of cosmic inflation, began to grow, pulling matter together and forming clumps of gas. The first stars would form when these clumps of gas grew dense enough for nuclear fusion to take place. The first stars were very different from the stars we see today. They were massive, hot, and incredibly bright, much larger and more energetic than modern stars. These stars formed from the hydrogen and helium gas that filled the universe, and they burned through their fuel quickly, living short, intense lives. But their role in the universe was critical. Not only did they light up the universe for the first time, but when they reached the end of their lives, they exploded in supernovae, spreading heavy elements like carbon, oxygen, and iron throughout the cosmos. These elements would go on to form new generations of stars, planets, and even life. It was these very first stars that began to shape the universe we know today. They created the heavy elements that would later form the planets, and their light began to break the cosmic darkness, allowing the universe to evolve into a dynamic, ever-changing place. Without these stars, life as we know it could never have formed. These first stars were so massive that some may have been hundreds of times the mass of our Sun. They would have shone with incredible brilliance, but their lives were brief candles in the cosmic night. After just a few million years, they would have exhausted their fuel and exploded, seeding the universe with the first heavy elements. The emergence of galaxies. As the first stars began to form, they didn't exist in isolation. They clumped together, pulled by gravity, to form the first galaxies. These early galaxies were small, irregular, and very different from the large spiral galaxies we see today. They were made up of the first generations of stars and gas, and they would serve as the building blocks for the much larger galaxies that would come later. The formation of galaxies was an essential step in the evolution of the universe. Galaxies are the structures that house stars, and they are the places where new stars are born. As these first galaxies merged and grew larger, they began to form the cosmic web we see today, vast structures made up of clusters of galaxies, separated by huge voids of empty space. It's a pattern that mirrors the distribution of matter in the early universe, with galaxies and clusters of galaxies connected by long filaments of dark matter and gas. Galaxies don't exist in isolation either. They interact, merge, collide. When two galaxies collide, It's not like cars crashing. The stars are so far apart that they mostly pass through each other, but the gas clouds collide and compress, triggering waves of new star formation. It's a creative destruction, chaos giving birth to new order. The cosmic dawn. The universe lights up. The formation of stars and galaxies mark the end of the cosmic dark ages and the beginning of what we call the cosmic dawn. This was the time when the universe first became populated with the bright shining stars that we are familiar with today. These stars, which emerged from the primordial hydrogen and helium, began to shape the universe, creating the building blocks for planets and galaxies. At this point, the universe became a much more dynamic and luminous place. The formation of stars began to provide the light needed for the evolution of more complex structures, and it eventually led to the creation of planets, moons, and everything else that would make up the galaxies we see today. This process took billions of years, but it all began with that crucial moment when the universe became transparent, allowing light to travel freely for the first time. That moment set the stage for the birth of stars and galaxies, and ultimately, for everything that followed. The light from these first stars also did something else important. It ionized the hydrogen gas around them, creating bubbles of ionized gas that grew and merged. This process, called reionization, transformed the universe once again, making it fully transparent to all wavelengths of light. It was like the universe waking up fully, opening its eyes to see clearly for the first time. The role of dark matter in structure formation. As we continue to talk about the formation of stars and galaxies, it's important to remember the role of dark matter. Even though we can't see it, dark matter plays an essential role in the formation of these structures. It doesn't emit light or energy, but it exerts gravity, which helps pull matter together. Without dark matter, the process of star and galaxy formation would have been much slower and more chaotic. Dark matter is thought to make up about 27% of the universe's total mass, and its influence is felt throughout the cosmos. It acts as the invisible scaffolding that helps structure the universe, guiding the formation of galaxies and clusters of galaxies. Without dark matter, the universe as we know it would look very different. We detect dark matter through its gravitational effects. When we look at how galaxies rotate, the outer edges are moving too fast. The visible matter isn't enough to hold them together at those speeds. There must be more mass there, mass we can't see. That's dark matter. When we look at how light bends around massive galaxy clusters, the bending is too extreme for the visible matter alone. Again, dark matter. The formation of the first stars and galaxies. An in-depth journey. Now that we've walked through the early moments of the universe, the cooling, the formation of atoms, and the first light, let's take a deeper dive into one of the most important chapters of the universe's story, the formation of the very first stars and galaxies. After the first atoms were formed and the universe became transparent, it entered the cosmic dark ages, a time when the universe was still largely empty, devoid of stars, and filled only with hydrogen and helium gas. It was a quiet, dark time, but not for long. Slowly, the universe began to come alive, thanks to the gravitational pull of matter and the processes that would eventually give birth to the stars and galaxies that fill our night sky today. Breathe deeply. Let yourself sink into this story. There's something deeply peaceful about understanding our cosmic origins, knowing that we're part of this vast ancient process. Gravity's role in star formation. The patient architect. To understand how the first stars formed, we need to look at the role gravity played in shaping the universe. Gravity is a powerful force, and even in the vast emptiness of space, it was pulling matter together. This force began to gather the hydrogen and helium gas that filled the universe into clumps. These clumps of gas became denser over time, and as gravity continued to pull the gas together, the gas began to collapse inward, forming protostars, the earliest stages of star formation. These protostars were dense regions of gas and dust, and as they collapsed, the pressure and temperature inside them began to rise. Eventually, when the temperature reached high enough levels, nuclear fusion could occur, marking the birth of a new star. These first stars were vastly different from the ones we see today. They were much larger, hotter, and more massive, burning through their fuel at an incredibly fast rate. In fact, many of them were so massive that they only lived for a few million years before exhausting their nuclear fuel and exploding in supernovae, the explosive deaths of stars. Gravity is patient. It works slowly but surely, drawing matter together grain by grain, atom by atom. Over millions of years, small differences in density grew larger. Regions that were slightly denser pulled in more matter, becoming denser still. This runaway process eventually created the first gravitationally bound structures in the universe. The first stars, a brilliant light in a dark universe. The birth of the first stars was a turning point in the history of the universe. For the first time, the universe was illuminated. These stars emitted light and energy, changing the universe from a dark, empty place to one filled with brilliant, shining beacons. These early stars were not just lights in the sky, they were crucial for the creation of the elements that make up the universe today. The first stars were mainly composed of hydrogen and helium, the elements created during the Big Bang. But over the course of their lives, these stars would undergo nuclear fusion, fusing hydrogen into helium, and in their final moments, even creating heavier elements like carbon, oxygen, and iron. These elements would later become the building blocks for planets, moons, and even life itself. When these massive stars reached the end of their lives, they exploded in supernovae, intense, violent bursts of energy that scattered their elements into the surrounding gas. These elements would eventually form the next generation of stars, planets, and galaxies. In a sense, the first stars were like cosmic factories, creating the very elements that would make the universe a more complex and dynamic place. A supernova is one of the most energetic events in the universe. For a brief moment, a single dying star can outshine an entire galaxy. The explosion is so powerful that it creates conditions extreme enough to forge the heaviest elements, things like gold, platinum, and uranium. Every gold ring, every piece of electronics with precious metals, contains atoms that were created in the violent death throes of ancient stars. The formation of the first galaxies, communities of stars. As the first stars formed, they didn't just remain isolated, they began to clump together, pulled by the force of gravity, forming the very first galaxies. A galaxy is a massive collection of stars, gas, and dust, all bound together by gravity. The first galaxies were smaller and less structured than the ones we see today, but they were the building blocks for the larger, more complex galaxies that would form later. These early galaxies were filled with the first generations of stars, and they played a crucial role in the evolution of the universe. The stars within them began to create the heavier elements like carbon, oxygen, and iron, that would later form planets and other celestial objects. As these galaxies grew, they began to interact with each other, merging and colliding, and creating new structures in the universe. The formation of galaxies also led to the creation of galaxy clusters, groups of galaxies bound together by gravity. These clusters would grow over time, and eventually, the universe would take on the large-scale structure that we see today. Vast regions of space filled with galaxies, all connected by dark matter and cosmic filaments. Galaxy formation is an ongoing process. Even today, we can observe galaxies merging and new galaxies forming. Our own Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, they'll merge to form a new, larger galaxy. It's a slow-motion cosmic dance that's been choreographed by gravity over billions of years. The cosmic web, a structured universe. As galaxies continue to form, They began to organize into a large-scale structure known as the cosmic web. The cosmic web is a vast network of galaxies, galaxy clusters and superclusters, all interconnected by dark matter and gas. This web-like structure is the framework of the universe, and it shows how galaxies are not randomly distributed, but instead form vast filaments and sheets that stretch across the cosmos. The cosmic web is not just a random arrangement of matter. It is the result of gravity acting over billions of years, pulling matter together into large structures. The vast voids between these filaments are mostly empty space, but the filaments themselves are densely packed with galaxies, stars, and dark matter. This structure is a direct consequence of the initial conditions set in the first moments after the Big Bang. The fluctuations in the density of matter, stretched by the rapid inflation of the universe, eventually grew into the large-scale structures that make up the cosmic web. And even today, galaxies and galaxy clusters continue to grow and evolve, forming new structures within this grand cosmic web. If you could see the universe from far enough away, stepping back to view the entire observable cosmos, you would see this web clearly. Galaxies clustered along filaments like beads on strings, vast empty voids between them, the whole thing looking remarkably like the neural network in a brain or the structure of a sponge. It's a pattern that repeats at different scales throughout nature. Supermassive black holes, a mysterious force in early galaxies. One of the most intriguing features of the first galaxies was the formation of supermassive black holes. These black holes, which are millions or even billions of times more massive than our Sun, are thought to have formed at the centers of the first galaxies. They are mysterious objects that exert a tremendous gravitational pull, and their origins are still not entirely understood. Scientists believe that supermassive black holes could have formed in the early universe through the collapse of massive clouds of gas, or through the merging of smaller black holes. These black holes are thought to play a crucial role in the evolution of galaxies. As gas and matter fall into them, they release enormous amounts of energy, and this energy can influence the growth and shape of the galaxy itself. The presence of supermassive black holes in the early universe is one of the great mysteries of cosmology. How did they form so quickly? And how did they influence the development of galaxies? These are questions that scientists are still working to answer, but they remind us that the early universe was a dynamic and complex place, full of phenomena that we are still trying to understand. When matter falls into a black hole, it doesn't just disappear quietly, it forms an accretion disk, a swirling disk of gas and dust that heats up to incredible temperatures as it spirals inward. This disk can shine brighter than all the stars in the galaxy combined, creating what we call a quasar. Quasars are some of the brightest objects in the universe, and they're powered by supermassive black holes feeding on surrounding matter. The interplay between stars and galaxies. As stars formed within galaxies, they began to interact with their environment in complex ways. Stars don't just passively exist within galaxies, they actively shape them. When massive stars explode as supernovae, they blast gas and dust outward at tremendous speeds. This can trigger new waves of star formation in nearby clouds, but it can also heat gas so much that it's blown completely out of the galaxy. This feedback mechanism helps regulate star formation. If stars form too quickly, they would use up all the available gas and the galaxy would go dark. But supernovae and stellar winds blow gas away, slowing down star formation and allowing it to continue at a sustainable rate over billions of years. Similarly, the supermassive black holes at galactic centers can affect star formation. When they're actively feeding, the energy they release can heat gas throughout the galaxy, preventing it from cooling and collapsing to form new stars. This creates a balance, a cosmic thermostat that regulates how galaxies grow and evolve. The chemical enrichment of the universe. With each generation of stars, the universe became chemically richer. The first stars contained only hydrogen and helium, but when they died, they scattered heavier elements into space. The next generation of stars formed from gas enriched with these elements, and they created even heavier elements when they died. This process of chemical enrichment continues today. Our Sun is a third or fourth generation star, formed from gas that had already been enriched by previous generations. That's why we have rocky planets like Earth. The first generation stars had no heavy elements to form planets from. Only later, after several generations of stars had lived and died, was there enough carbon, silicon, oxygen, and iron to build rocky worlds. This means that life as we know it could not have emerged in the early universe. There were no rocky planets, no complex chemistry, no possibility for biological evolution. Life had to wait, had to be patient, until the universe had been enriched enough with heavy elements. We are not just made of stardust, we are made of the ashes of multiple generations of stars, the evolution of galaxy morphology. As galaxies grew and evolved, they began to take on different shapes and structures. Some became grand spiral galaxies with elegant arms swirling around a central bulge. Others became elliptical galaxies, smooth and featureless. Still others remained irregular, without any particular structure. What determines a galaxy's shape? It's a complex question involving the galaxy's formation history, its interactions with other galaxies, and the amount of gas available for star formation. Spiral galaxies tend to be actively forming stars, with bright young stars lighting up their spiral arms. Elliptical galaxies are usually older, with most of their star formation in the distant past, populated by older, redder stars. When galaxies collide and merge, they can lose their spiral structure, forming ellipticals. But mergers can also trigger intense bursts of star formation as gas clouds collide and compress. These starburst galaxies can form stars hundreds of times faster than normal galaxies, though they exhaust their gas supplies quickly. The ongoing story. And so the universe continued to evolve, generation after generation of stars living and dying, galaxies growing and merging, structure building upon structure. From that initial singularity, through cosmic inflation, through the formation of atoms and the cosmic dark ages, to the first stars and galaxies, the universe has been on an incredible journey. The journey continues. Right now, at this very moment, new stars are being born in stellar nurseries throughout the cosmos. Galaxies are colliding and merging. Black holes are feeding and growing. The universe is still expanding, still evolving, still writing its story. And we are part of that story. We are the universe become conscious, able to look back and understand its own history, from the Big Bang to this moment, from hydrogen atoms to human beings. It's all one continuous story, one magnificent unfolding of cosmic evolution. Stellar evolution and element creation. As the first stars lived and died, they created the building blocks for the next generations of stars and galaxies. Stellar evolution is the process by which a star forms, lives, and eventually dies, and during this process, stars create the elements that make up the universe. The lightest elements, hydrogen and helium, were formed in the Big Bang, but everything heavier, carbon, oxygen, iron, was created inside stars. Stars begin their lives by fusing hydrogen into helium in their cores. This process, known as nuclear fusion, releases vast amounts of energy, which is what makes stars shine. Over the course of their lives, stars go through different stages of fusion, creating heavier and heavier elements. For example, when a star runs out of hydrogen, it begins fusing helium into carbon. Later in its life, it may even fuse carbon into heavier elements, such as oxygen and iron. When these stars die, especially the most massive ones, they explode in supernovae, scattering these newly created elements into the surrounding gas. This process not only enriches the universe with heavier elements, but also triggers the formation of new stars, planets, and even life. Without these supernovae, the universe would have remained a barren place, without the complex elements needed for life to exist. The legacy of the first stars and galaxies. The first stars and galaxies were truly the architects of the universe, as we know it today. These cosmic pioneers created the elements that would become the building blocks of everything we see around us. They generated the light that pierced through the darkness of the early universe, and they formed the structures that allowed the cosmos to evolve from a chaotic, uniform place into the complex and beautiful system of stars, galaxies, and planets we observe today. The birth of these first stars marked a pivotal turning point in cosmic history. It was the beginning of the universe's dynamic nature, setting in motion a process that continues to this day as new stars are born from clouds of gas and dust, while old ones die in spectacular explosions. This cosmic cycle has been repeating itself for billions of years, constantly reshaping and enriching the universe. Without the first stars and galaxies, our existence would simply not be possible. There would be no Earth to call home, no sun to warm our planet, and certainly no life to contemplate these cosmic mysteries. In a very real and profound sense, we are all intimately connected to those first stars. Every atom in our bodies, except for hydrogen, was forged in the hearts of those ancient blazing suns. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was created inside stars that died billions of years ago. We are stardust, literally created by the very first stars that illuminated the darkness of the early universe. We owe our existence not just to their brilliant light, but also to their dramatic deaths. When these massive stars exploded as supernovae, they scattered their newly created elements across space, seeding the cosmos with the raw materials needed to form planets and eventually life itself. It's a humbling and awe-inspiring realization that connects us to the deepest reaches of space and time. The expansion of the universe and Hubble's discovery. Now that we've walked through the fascinating story of the formation of stars and galaxies, it's time to take a step back and look at an even bigger picture. The universe is not just a static backdrop against which stars and galaxies perform their cosmic dance. Instead, it's a dynamic, ever-changing system that has been expanding since the moment of the Big Bang. The idea that the universe itself is expanding might sound a little strange at first, perhaps even counterintuitive, but it's one of the most important and revolutionary discoveries in the entire field of cosmology. This groundbreaking revelation all began with a remarkable observation by the American astronomer Edwin Hubble, whose work would forever change our understanding of the cosmos and our place within it. The expanding universe, a surprising discovery. For much of human history, spanning thousands of years across different cultures and civilizations, we believed that the universe was static. This wasn't just a casual assumption, but a deeply held conviction that the cosmos was fixed and unchanging. People thought the stars, planets, and galaxies were essentially locked in their places, staying where they had always been since time immemorial. The universe was seen as eternal and unchanging, a perfect and immutable creation. But that ancient idea was completely shattered in the 1920s, thanks to the meticulous work of Edwin Hubble. Working at the Mount Wilson Observatory in California, Hubble made a remarkable discovery when he observed distant galaxies using one of the most powerful telescopes of his time. What he found was absolutely astonishing and would revolutionize our understanding of the cosmos. Hubble discovered that galaxies were moving away from us, but it wasn't just that they were moving. What was truly remarkable was the pattern he observed. The farther away a galaxy was from us, the faster it seemed to be moving away. This wasn't random motion, but a clear, predictable relationship between distance and velocity. This discovery is now known as Hubble's law, and it provided the first concrete evidence that the universe is expanding. At first glance, this might sound like a simple observation, just another interesting fact about the cosmos. but it had profound and far-reaching implications that would reshape our entire understanding of the universe. Hubble's discovery gave scientists the first clear observational evidence that the universe is not static, but is instead constantly stretching, expanding outward in all directions. This meant that the universe had a history, that it was changing over time, and that it must have had a beginning. The concept of an expanding universe. Now, to truly understand this expansion, we need to think carefully about the fabric of space itself. This is where things get really interesting and perhaps a bit mind-bending. The idea behind the expansion of the universe is not that galaxies are simply moving through space like cars driving on a highway or boats sailing across an ocean. That would be too simple and wouldn't capture the true nature of what's happening. Instead, space itself is expanding. Let me give you a helpful analogy to visualize this concept. Imagine the surface of a balloon with dots drawn on it to represent galaxies. As you inflate the balloon, what happens? The dots move away from each other, not because they're moving across the surface, but because the surface itself is stretching and expanding. The dots aren't traveling through the rubber of the balloon. The rubber between them is simply growing, pushing them apart. This is remarkably similar to what happens with galaxies in our universe. As space itself expands, galaxies move farther apart from each other. They're not racing through space at incredible speeds. Rather, the space between them is growing, carrying them along for the ride. It's a subtle but crucial distinction that helps us understand the true nature of cosmic expansion. This expansion of space is not just happening locally in our neighborhood of the cosmos. It's happening everywhere simultaneously. Every galaxy in the observable universe is receding from every other galaxy, and the farther away a galaxy is, the faster it appears to be moving away from us. It's like a vast cosmic stretching that affects the entire universe at once, and remarkably, it has been happening continuously since the very first moment of the Big Bang. This profound realization that the universe is expanding was a major turning point in our understanding of the cosmos. It strongly suggested that the universe must have had a beginning, a specific moment in time when everything was compressed into an incredibly small, dense point of infinite temperature and density. This point, of course, was what we now call the Big Bang, the moment when space, time, matter, and energy all came into existence. Hubble's law, a window into the past. Hubble's discovery didn't just tell us that the universe is expanding in the present moment. It also provided scientists with a powerful tool to begin measuring the age of the universe itself. By carefully studying the rate of expansion and working backward, like running a movie in reverse, scientists could estimate how long the universe had been expanding since its beginning. This calculation, refined over decades with increasingly precise measurements, pointed to a universe that was approximately 13.8 billion years old. The universe's expansion provided astronomers with a kind of cosmic clock, a natural timepiece that allowed us to look back through time and understand the history of everything that exists. Here's how this works in more detail. The more distant a galaxy is from us, the more its light is redshifted. This phenomenon, known as redshift, happens because as light travels through an expanding universe over billions of years, the wavelengths of that light get stretched along with space itself. This stretching causes the light to shift toward the red end of the electromagnetic spectrum, hence the name redshift. By carefully measuring how much redshift occurs in the light from distant galaxies, astronomers can determine two crucial pieces of information. First, they can calculate how far away those galaxies are from us. Second, they can determine how fast they are receding, moving away from us as space expands. The relationship between these two measurements, distance and recession velocity, is what we call Hubble's law. This was an incredibly important breakthrough because it provided further powerful evidence for the Big Bang theory. Think about it logically. If the universe is expanding today, and galaxies are moving away from each other in all directions, it means that at one point in the past, they must have been closer together. If we go back far enough in time, all matter and energy in the universe must have been concentrated in a single, infinitesimally small point. This moment, this singularity, marked the beginning of the universe as we know it, and the expansion that began then continues even now, billions of years later. Cosmic expansion and the Hubble Space Telescope. Edwin Hubble's pioneering work in the 1920s laid the foundation for modern cosmology, establishing the basic framework for how we understand the universe. But it wasn't until much later, decades after his initial discovery, that we were able to gather even more detailed and precise information about the expanding universe through advanced space-based telescopes. The most famous of these is the Hubble Space Telescope, named in honor of Edwin Hubble himself. Launched in 1990 and placed in orbit above Earth's atmosphere, this remarkable instrument revolutionized our understanding of the universe by providing incredibly detailed, crystal-clear images of distant galaxies, colorful nebulae, and countless other cosmic phenomena that would be impossible to see clearly from the ground. The Hubble Space Telescope has allowed astronomers to observe galaxies farther away than ever before imagined, giving us a much better understanding of how the universe has evolved over billions of years of cosmic history. One of the most exciting and scientifically valuable discoveries that the Hubble Space Telescope has helped us make is the observation of distant galaxies that formed just a few 100 million years after the Big Bang. These early galaxies, seen as they appeared in the universe's infancy, give us an unprecedented glimpse into a time when the cosmos was young and the first generation of galaxies and stars were just beginning to come together. By studying these ancient galaxies, astronomers can piece together the story of how simple structures grew into the complex cosmic web of galaxies we see today. Understanding the rate of expansion, the role of dark energy. As we talk about the universe's expansion, it's crucial to note something truly surprising that scientists discovered relatively recently. Not only is the universe expanding, but the rate of expansion is actually accelerating, getting faster over time. This discovery was made in the late 1990s, and it came as a complete shock to the scientific community, turning our understanding of cosmic expansion on its head. In fact, for many decades before this discovery, scientists believed quite confidently that the expansion of the universe must be slowing down. This made intuitive sense based on our understanding of gravity. After all the matter in the universe, including galaxies, stars, planets, and dark matter, exerts gravitational pull on everything else. Gravity is always attractive, always pulling things together, so logically, it should be acting like a brake on the universe's expansion, gradually slowing it down over time. But in 1998, two independent teams of astronomers studying distant supernovae, massive stellar explosions that can briefly outshine entire galaxies, discovered something completely unexpected and frankly puzzling. The universe was not slowing down as everyone had assumed. Instead, it was actually accelerating, expanding faster and faster as time went on. This was like discovering that a ball you threw up into the air, instead of slowing down due to gravity, was actually speeding up as it rose. This bizarre acceleration is thought to be caused by something mysterious and poorly understood called dark energy. Dark energy is a hypothetical force or property of space that makes up approximately 68% of the total energy content of the universe. That means more than 2/3 of everything in the universe is this strange, invisible energy we barely understand. Dark energy is thought to be responsible for the accelerated expansion of the universe, though we still don't fully understand what it actually is, where it comes from, or exactly how it works. What we do know from observations is that dark energy has a repulsive effect, the opposite of gravity. It's pushing galaxies apart, accelerating the expansion of space itself, counteracting gravity's attempt to pull everything together. The more space expands, the more dark energy there is, creating a kind of runaway effect that causes the expansion to accelerate ever faster. The fate of the expanding universe, will it expand forever? Now that we know the universe is expanding, and that this expansion is actually accelerating, it raises another deeply interesting and philosophically profound question. What's next for the universe? What does the future hold for the cosmos? Will it continue to expand forever, eternally growing larger and larger, or is there a limit to how far it will stretch? Could something eventually stop or even reverse this expansion? Scientists have come up with several fascinating possibilities based on the current rate of expansion, the amount of matter and energy in the universe, and particularly the mysterious nature and behavior of dark energy. Let's explore these different scenarios for the ultimate fate of our universe. One possibility, and currently the most widely accepted scenario based on our observations, is that the universe will keep expanding forever. In this scenario, galaxies will grow farther and farther apart over incredibly long timescales, separated by ever-increasing gulfs of empty space. If this happens, the universe will continue to cool gradually as it expands, becoming increasingly dark over time as stars burn out their nuclear fuel and no new stars can form due to the lack of raw materials. This scenario is known as the Big Freeze or heat death, and it represents a slow, gradual decline into an ever colder and darker universe. Imagine a cosmos where trillions of years from now, the last stars have flickered out, galaxies are so far apart they can no longer see each other, and the universe is a cold, dark, nearly empty void. Another intriguing possibility is that the expansion could eventually slow down, come to a complete stop, and then reverse direction, leading to what's called the Big Crunch. In this scenario, which would require dark energy to somehow weaken or disappear, the universe's expansion would gradually slow as gravity eventually becomes dominant again and pulls all matter back together. Galaxies, stars, and planets would begin falling toward each other, and eventually the universe would collapse, contracting back to a state similar to the incredibly dense singularity that existed before the Big Bang. Everything would be crushed together in a final cosmic implosion. There's also a more dramatic and somewhat terrifying possibility called the Big Rip. In this scenario, the acceleration of the universe's expansion increases so dramatically over time that the mysterious force of dark energy becomes overwhelmingly strong. Eventually, it would become so powerful that even the fundamental forces of nature that hold matter together, forces like gravity and electromagnetism, would be overwhelmed and torn apart. In a Big Rip scenario, first galaxies would be ripped apart as the space between stars expands faster than gravity can hold them together. Then solar systems would be torn apart as planets are ripped away from their stars. Eventually, even planets themselves would be shredded. And finally, in the last moments before the Big Rip, even atoms would be torn apart as the space between atomic nuclei and electrons expands faster than electromagnetic forces can maintain. It would be a violent and dramatic end to everything. Right now, based on our best observations and measurements, we don't know for certain which scenario will actually unfold. However, the accelerating expansion that we currently observe, driven by the mysterious dark energy, suggests that the universe could very well keep stretching outward for an incredibly long time, perhaps forever, with galaxies gradually drifting further and further apart into the cosmic darkness. Looking back to the beginning, the cosmic horizon, Hubble's groundbreaking discovery not only opened up a completely new understanding of the expanding universe and its future, it also gave us a remarkable gift, the ability to look back in time itself. This might sound like science fiction, but it's a very real consequence of the finite speed of light combined with the vast distances in space. Here's how it works. Light travels incredibly fast, moving at about 300,000 kilometers per second, but it's not infinitely fast, because light from distant galaxies takes time to travel across the universe to reach us. When we observe these faraway galaxies through our telescopes, we are not seeing them as they are now in the present moment. Instead, we are seeing them as they were in the past, when the light we're detecting actually left them. The farther away a galaxy is from us, the longer its light has been traveling through space to reach our telescopes, and therefore, the further back in time we are looking when we observe it. A galaxy that's 1 billion light-years away is seen as it was 1 billion years ago. A galaxy 10 billion light-years away shows us what it looked like 10 billion years ago, when the universe was much younger. This remarkable property means that by studying the farthest, most distant galaxies we can detect, we can look back almost to the very beginning of the universe itself, to a time shortly after the Big Bang when the first stars and galaxies were just beginning to form. It's like having a cosmic time machine that lets us witness the universe's history directly. But there's a fundamental limit to how far we can see, known as the cosmic horizon or observable universe. This limit exists because the universe has a finite age of about 13.8 billion years. Light from anything farther away than roughly 46 billion light-years, accounting for expansion, simply hasn't had enough time to reach us since the Big Bang occurred. Beyond this cosmic horizon, the universe may continue for vast distances, perhaps infinitely, but that region is not observable to us because the light from those regions hasn't reached us yet, and may never reach us if expansion continues to accelerate. In a very real way, this gives us an incredible window into the early universe, a way of directly observing and studying the time when the cosmos was first forming, when the first stars and galaxies were just beginning to take shape from clouds of primordial hydrogen and helium gas. And as our technology continues to improve with new telescopes like the James Webb Space Telescope, we'll be able to see even farther into the past, bringing us closer and closer to observing the Big Bang itself and understanding those first critical moments of cosmic history. The ongoing expansion, what lies ahead. As we continue to study the expanding universe with increasingly sophisticated instruments and techniques, we're left with many profound and challenging questions that keep cosmologists awake at night. Will the universe truly continue to expand forever, growing ever larger and colder? Will dark energy continue its mysterious work, relentlessly pushing galaxies apart at ever-increasing speeds? Or will something unexpected happen? Could the universe eventually slow down and collapse back into a singularity, perhaps triggering another Big Bang in an endless cycle of cosmic rebirth? These are the deep questions that cosmologists and astrophysicists around the world are working tirelessly to answer. Each new discovery, each more precise measurement of cosmic expansion, brings us incrementally closer to understanding the true nature of the universe and its ultimate fate. The universe is an incredibly vast and complex place, almost incomprehensibly large and filled with mysteries we're only beginning to unravel. We've only just begun to scratch the surface of its deepest secrets. The expansion of the universe, first discovered by Edwin Hubble nearly a century ago, is one of the most profound and far-reaching discoveries in the entire history of science. It's a discovery that not only fundamentally changed our understanding of the universe's past, revealing that it had a beginning rather than existing eternally, but also set the stage for all the fascinating questions we still have about its future and ultimate destiny. Dark matter and dark energy, the invisible forces. As we've already discussed in previous sections, the universe is full of fascinating visible phenomena that capture our imagination and fill us with wonder, from the beautiful spiral arms of galaxies and the brilliant light of stars to the rocky surfaces of planets and the colourful glowing clouds of nebulae where new stars are born. There's no shortage of spectacular cosmic sights to observe and study. But for all the amazing things we can see with our eyes and telescopes, there are vast regions and components of the cosmos that remain mysterious, invisible to our instruments, and impossible to observe directly with any form of light or electromagnetic radiation. These invisible forces and substances, known as dark matter and dark energy, actually make up the vast majority of everything that exists in the universe. Despite constituting roughly 95% of the universe's total mass and energy content, we know very little about their true nature. They remain two of the deepest mysteries in modern science. Yet, despite our incomplete understanding, their influence is absolutely critical to the structure, behavior, and ultimate fate of the universe. Without them, the cosmos would look completely different, and we wouldn't be here to observe it. Let's take a closer and more detailed look at these two elusive forces and try to understand their profound role in shaping the cosmos. Dark matter, the unseen matter that holds the universe together. First, let's explore dark matter in depth. This is the invisible substance that exerts a gravitational pull on everything in the universe, acting like an invisible cosmic scaffold that holds structures together. Scientists have known about the existence of dark matter for nearly a century now, though its true nature and composition remain one of the most profound and frustrating mysteries in modern physics and astronomy. You may be wondering at this point, if dark matter is completely invisible and doesn't interact with light, how do we even know it exists? How can scientists be so confident about something they can't see? That's an excellent and very reasonable question. The answer lies in understanding the way dark matter affects the visible universe through its gravitational influence. While dark matter doesn't emit any light of its own, doesn't absorb light passing through it, and doesn't reflect light like a mirror, making it completely invisible to all our telescopes regardless of what wavelength we look at, we can detect its presence indirectly by carefully observing how it interacts with visible matter and energy through the force of gravity. Gravity affects everything with mass, whether visible or invisible, and dark matter has plenty of mass, even though we can't see it. One of the first important clues that led scientists to hypothesize the existence of dark matter came from detailed studies of how galaxies rotate. This discovery was pioneered in the 1970s by astronomer Vera Rubin and her colleagues, when they carefully measured the rotational speeds of stars at different distances from the centers of spiral galaxies. They noticed something very strange and unexpected. According to Newton's laws of gravity and our understanding of orbital mechanics, stars at the outer edges of a galaxy should be moving slower than those near the center. This is because they're farther away from the galaxy's center of mass, where most of the visible matter like stars and gas is concentrated. Just like planets farther from the sun move more slowly in their orbits, outer stars in a galaxy should also move more slowly. But that's not what astronomers observed when they actually measured these speeds. To everyone's surprise, the stars at the outer edges of galaxies were moving just as fast, and sometimes even faster, than the ones near the center. This didn't make sense based on the visible matter alone. The only way to explain this observation was to conclude that there was more mass in galaxies than could be accounted for by just the visible stars, glowing gas and dust that we could see with our telescopes. This extra invisible mass was providing additional gravitational pull, keeping the outer stars moving faster than expected. This unseen mass was dubbed dark matter. Dark matter doesn't interact with light or any form of electromagnetic radiation in the way normal matter does, which is precisely why it remains invisible to us. However, it definitely has mass, and wherever there's mass, there's gravity. This invisible dark matter is responsible for providing the extra gravitational pull that keeps galaxies from flying apart due to the high speeds of their rotating stars. Without dark matter holding them together with its gravity, galaxies would simply tear themselves apart, with stars flying off into intergalactic space. The universe would look completely different, and galaxies as we know them wouldn't exist. Current estimates suggest that dark matter makes up approximately 27% of the universe's total mass and energy content. To put this in perspective, in other words, the vast majority of all the mass in the entire universe is made of something we can't see, can't touch, and can't directly detect with any of our instruments or sensors. But we know beyond any doubt that it's there, because of its unmistakable gravitational influence on all the things we can observe, from the rotation of galaxies to the motion of galaxy clusters to the large-scale structure of the cosmos itself. What is dark matter made of? Despite many decades of intensive research, numerous experiments, and countless hours of telescope observations, scientists still don't know exactly what dark matter is actually made of at the fundamental particle level. It's frustrating in a way, knowing that most of the universe's mass is made of something we can't identify. Several theories and hypotheses have been proposed over the years, each with its own supporting evidence and challenges, but none have been definitively confirmed yet through direct detection or experiment. The most widely accepted and studied idea is that dark matter is composed of weakly interacting massive particles, commonly abbreviated as WIMPs. These hypothetical particles are thought to interact only very weakly with regular, ordinary matter through forces other than gravity. They would rarely collide with or affect normal atoms, which is why they're so difficult to detect, even though they might be passing through us all the time. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays, trying to catch even a single interaction between a WIMP and a normal atom, but so far these searches have come up empty-handed. Another intriguing possibility that has gained attention is that dark matter could be made up of extremely light particles called axions. These theoretical particles were originally proposed to solve a different problem in particle physics, but it turns out they could also make good dark matter candidates. Axions are predicted to be extraordinarily light, much lighter than even electrons, and wouldn't interact with other particles in the way we typically think about particle interactions. Their ghostly nature would make them extremely difficult to detect, requiring specialized experiments with incredibly sensitive equipment. There are also more exotic theories that suggest dark matter might not be made of particles at all, at least not in the conventional sense. Some scientists have proposed that dark matter could be composed of primordial black holes, which are black holes that formed very shortly after the Big Bang from density fluctuations in the early universe, rather than from the collapse of stars. These primordial black holes could range in size from smaller than an atom to many times the mass of the Sun, and they could account for some or all of the extra gravitational effects we observe and attribute to dark matter. Some researchers have even questioned whether dark matter exists as a substance at all, suggesting instead that our understanding of gravity might need to be modified at galactic scales. These modified gravity theories, like Mund-modified Newtonian dynamics, attempt to explain galactic rotation curves without invoking dark matter. However, these theories have struggled to explain all the observations as successfully as dark matter does, particularly observations of colliding galaxy clusters and the cosmic microwave background radiation. No matter what dark matter ultimately turns out to be made of, whether it's WIMPs, axions, primordial black holes, or something we haven't even thought of yet, we know one thing for absolutely certain based on overwhelming observational evidence. It exists in vast quantities throughout the universe, and it has a profound influence on the structure, formation, and behavior of everything we can see. Without dark matter providing its gravitational scaffolding, galaxies, stars, and planets, as we know them today, would not exist. Dark matter is the invisible glue that holds the visible universe together, the hidden framework upon which all cosmic structure is built. Dark energy. The mysterious force behind the universe's acceleration. Now that we've talked extensively about dark matter and its role in holding cosmic structures together, let's move on to discuss dark energy, an even more mysterious and perplexing force that seems to be doing exactly the opposite. While dark matter acts like cosmic glue, using gravity to pull matter together into galaxies and galaxy clusters, dark energy is a cosmic anti-gravity force that is pushing the entire universe apart at an ever-increasing rate. Unlike dark matter, which pulls matter together with gravity and helps form the structures we see in the universe, dark energy seems to do the opposite. It creates a kind of repulsive force that pushes galaxies apart and accelerates the expansion of space itself. The discovery of dark energy is one of the most surprising and important findings in cosmology in recent decades, and it completely changed our understanding of the universe's fate. The discovery of dark energy came in 1998 through the independent work of two teams of astronomers who were studying distant Type Ia supernovae. These particular supernovae are extremely useful for cosmic measurements because they have a very consistent brightness, making them what astronomers call standard candles that can be used to measure vast distances across the universe. These teams were expecting to measure how much the universe's expansion had slowed down over billions of years due to the gravitational pull of all the matter in the cosmos. But instead, they found something completely unexpected and frankly shocking. The distant supernovae appeared fainter than they should have been. Based on the predictions, this could only mean one thing: they were farther away than expected, which suggested that the universe wasn't just expanding, but that the expansion was actually accelerating, getting faster over time. At first, scientists were completely baffled by this result. They checked and rechecked their measurements, worried they had made an error. For many decades before this discovery, cosmologists had confidently thought that the expansion of the universe would naturally slow down over time due to the gravitational pull of all the matter and dark matter in the universe pulling back against the expansion. But this new, careful observation showed exactly the opposite. The expansion was speeding up, not slowing down. This mysterious force that seemed to be driving the acceleration of the universe's expansion needed a name, and scientists called it dark energy, in part because, like dark matter, it seems to be invisible and doesn't interact with light, and in part because they really had no idea what it actually was. It's now believed, based on multiple lines of observational evidence, including supernovae studies, measurements of the cosmic microwave background radiation, and observations of the large-scale structure of the universe, that dark energy makes up approximately 68% of the total energy content of the entire universe. So, just like dark matter, which constitutes most of the mass, dark energy constitutes most of the energy. Together, dark matter and dark energy make up about 95% of everything in the universe, leaving only about 5% as the ordinary matter that makes up stars, planets, and everything we can directly observe. However, unlike dark matter, which has mass and exerts a gravitational pull that attracts matter, dark energy has a repulsive effect. It generates a kind of negative pressure or anti-gravity force that causes the fabric of space itself to expand faster and faster over time. The more space expands, the more dark energy there seems to be, creating a feedback loop that leads to ever faster expansion. What is dark energy? Like dark matter, dark energy is one of the biggest and most frustrating mysteries in modern cosmology and physics. We don't know exactly what it is, what causes it, or why it exists in the first place. It's extremely difficult to study directly because it doesn't interact with matter or light in any way that we can easily detect or measure. We only know about it through its large-scale effects on the expansion of space itself. Some theoretical models suggest that dark energy could be related to the energy of empty space itself, a fascinating concept known as vacuum energy. According to quantum field theory, even the vacuum of space is not truly empty at all. Instead, it's filled with quantum fluctuations, virtual particles constantly popping in and out of existence, and various quantum fields permeating all of space. This quantum activity could give empty space a baseline energy, and this energy could be what we observe as dark energy, causing space to expand. The problem is that when physicists try to calculate how much vacuum energy there should be based on quantum mechanics, they get an answer that's wrong by a truly enormous factor, something like 120 orders of magnitude too large. This is arguably the worst prediction in the history of physics, and it suggests that either our understanding of quantum mechanics or our understanding of gravity, or both, needs major revision. Another possibility that has been seriously considered is that dark energy could be the result of what's called a cosmological constant, a concept that has an interesting history. This term was originally introduced by Albert Einstein in his theory of general relativity. When Einstein first developed his equations describing gravity and the structure of space-time, he added this constant to his equations to allow for a static, unchanging universe, which was what people believed existed at the time. However, after Edwin Hubble's discovery that the universe was actually expanding, Einstein removed the cosmological constant from his equations, reportedly calling its addition his greatest blunder. But ironically, the recent discovery of dark energy and the accelerating expansion of the universe has revived Einstein's cosmological constant. It turns out he may have been right after all, just for reasons he never imagined. The cosmological constant could represent a fundamental property of space itself, an intrinsic energy density that remains constant as the universe expands, causing that expansion to accelerate. There are also more exotic possibilities being explored by theoretical physicists. Some researchers have proposed that dark energy might not be constant over time, but could instead be a dynamic field called quintessence that changes slowly as the universe evolves. Others have suggested that dark energy might not be a new form of energy at all, but rather a sign that our understanding of gravity breaks down at cosmological scales and needs to be modified. Despite all these theories and countless research papers, dark energy remains fundamentally an enigma. We know it exists because we can measure its effects on cosmic expansion. We know it's responsible for the accelerated expansion of the universe, pushing galaxies apart at ever-increasing speeds. But we don't yet understand its true nature, its origin, or why it has the strength it does. Just as dark matter reveals the invisible framework and scaffolding that holds galaxies and galaxy clusters together, dark energy is shaping the very future of the cosmos, determining whether the universe will expand forever or eventually meet some other fate. The fate of the universe. Will dark energy lead to the Big Freeze? The presence and dominance of dark energy in the universe raises an intriguing and profound question about the ultimate destiny of everything that exists. What will happen to the universe in the very long run, trillions upon trillions of years from now? If dark energy continues to accelerate the expansion of the universe indefinitely, as current observations suggest it will, it could lead to a future that's both fascinating and somewhat melancholy. In this scenario, galaxies will be pulled farther and farther apart over unimaginably long timescales. Eventually, the distances between galaxies will become so vast that they will no longer be able to see each other. The light from distant galaxies will be redshifted so severely that it becomes undetectable. Individual galaxies will exist in isolation, cosmic islands in an ever-expanding ocean of space. As this expansion continues relentlessly, stars will gradually burn out as they exhaust their nuclear fuel. New star formation will slow and eventually cease entirely as galaxies run out of the gas needed to create new stars. The universe will become progressively colder, darker, and emptier over time. This bleak future is what cosmologists call the Big Freeze or heat death of the universe. This scenario suggests that as the universe continues its accelerated expansion, stars will eventually all burn out completely. Galaxies will drift away from each other into the lonely darkness. Space between cosmic objects will become increasingly empty and cold. The universe will eventually become a dark, cold, desolate place, with only the fading remnants of once brilliant galaxies scattered across incomprehensible distances. All the processes that once fueled life and light will have long since ceased. It's a slow, gradual decline spanning timescales that dwarf the current age of the universe many times over. This is currently the most widely accepted theory about the ultimate fate of the universe, based on our best observations and understanding. But there are other possibilities that we can't completely rule out yet. If dark energy were to somehow change its behavior over time, which we can't predict with certainty, It could potentially lead to an even more dramatic scenario called the Big Rip. In this terrifying possibility, the expansion of the universe would accelerate so dramatically that eventually even the fundamental forces of nature that hold matter together would be overwhelmed and torn apart. First, galaxy clusters would be torn apart. Then individual galaxies would be ripped to shreds. Then solar systems would be destroyed. Eventually, even planets, molecules, atoms, and finally even atomic nuclei would be torn apart in the final moments before the Big Rip. It would be a violent and catastrophic end to everything, though fortunately, this scenario is considered less likely based on current observations. Alternatively, if the effects of dark energy were somehow to reverse or weaken over time, outcome we cannot currently predict with confidence, the expansion of the universe could eventually slow down and even reverse. This would lead to what cosmologists call the Big Crunch, a scenario where the universe eventually collapses back in on itself. In this dramatic possibility, gravity would ultimately triumph over dark energy, pulling all matter and energy back together into an incredibly dense, hot state similar to the conditions that existed at the moment of the Big Bang. Some theorists have even speculated that such a collapse could potentially trigger a new Big Bang, creating a cyclic universe that goes through endless iterations of expansion and contraction, birth and death, over and over again throughout eternity. For now, the future of the universe remains fundamentally uncertain, though the evidence we have gathered points most strongly toward the Big Freeze scenario. But what we do know with considerable confidence is that dark matter and dark energy are two of the most important and influential forces shaping the universe's past, present, and future. Together, they account for approximately 95% of the universe's total mass energy content, leaving only about 5% as the ordinary matter that makes up everything we can see and touch. Despite constituting such a small fraction of the cosmos, we ordinary matter inhabitants get to observe and ponder the mysteries of the vast invisible universe that surrounds us. These mysterious dark components influence everything from the formation and structure of galaxies to the ultimate fate of the entire cosmos. They are the hidden architects of the universe, working behind the scenes to shape reality in ways we are only beginning to understand. The search for answers: how do we study dark matter and dark energy? Studying dark matter and dark energy is extraordinarily challenging, perhaps one of the most difficult tasks in all of science, because neither of these mysterious forces interacts with light or any form of electromagnetic radiation in any directly detectable way. Scientists have had to become incredibly creative and ingenious in developing methods to study them indirectly. It's like trying to study an invisible person by watching how they interact with their surroundings, observing the footprints they leave and the objects they move rather than seeing them directly. For dark matter, the primary method of detection relies on looking for its gravitational effects on visible matter, the things we can actually see with our telescopes. Scientists carefully observe how stars move within galaxies, how galaxies move within galaxy clusters, and how light from distant objects is bent and distorted as it passes through regions containing large amounts of dark matter through a phenomenon called gravitational lensing. Gravitational lensing is particularly fascinating and useful. According to Einstein's theory of general relativity, massive objects bend and warp the fabric of space-time around them, and this warping affects the path that light takes as it travels through space. When light from a distant galaxy passes near a massive concentration of dark matter, its path is bent, causing the background galaxy to appear distorted, magnified, or even multiply-imaged. By carefully studying these lensing effects, astronomers can map out where dark matter is located and estimate how much of it is present, even though they can't see the dark matter itself. For dark energy, the approach is somewhat different, but equally indirect. Scientists study the expansion of the universe and measure how this expansion has changed over cosmic history by observing distant objects at various distances and therefore various times in the past. By carefully analyzing the light from distant supernovae, measuring the patterns in the cosmic microwave background radiation left over from the Big Bang, and surveying the large-scale distribution of galaxies across the universe, astronomers can piece together how fast the universe is expanding at different epochs and determine that this expansion is indeed accelerating. Scientists are also working tirelessly on a wide variety of sophisticated experiments and advanced observational tools to gather more data and hopefully unlock the mysteries of these invisible forces. The effort spans multiple approaches and technologies, from particle physics to astronomy to fundamental theoretical work. For example, one of the most promising and expensive tools for potentially detecting dark matter particles directly is the Large Hadron Collider, or LHC, located underground along the border between France and Switzerland. This massive machine is the world's largest and most powerful particle accelerator, a circular tunnel 27 kilometers in circumference, where protons are accelerated to nearly the speed of light and then smashed together with tremendous energy. By colliding particles together at these incredibly high energies, scientists hope to recreate conditions similar to those that existed in the very early universe. Shortly after the Big Bang, if dark matter particles like WIMPs can be created in these high-energy collisions, sensitive detectors surrounding the collision point might be able to observe them, or at least observe their effects on other particles. Even if dark matter particles themselves escape detection, their presence might be inferred by carefully accounting for all the energy and momentum in the collision and noticing when some goes missing. In addition to the LHC, there are numerous dark matter detection experiments located deep underground in mines and tunnels around the world. These experiments use extremely sensitive detectors, cooled to near absolute zero and shielded from cosmic rays by thousands of feet of rock, trying to catch the incredibly rare event of a dark matter particle colliding with an atomic nucleus. Despite years of operation and remarkable sensitivity, these experiments have not yet definitively detected dark matter particles, but they continue to push the boundaries of what's possible and set ever tighter constraints on the properties dark matter particles must have. Astronomical observations continue to provide crucial information as well. Advanced telescopes, both on the ground and in space, are constantly gathering data that helps us understand dark matter and dark energy better. The Hubble Space Telescope, despite being over 3 decades old, continues to make important observations of distant supernovae, gravitational lensing, and the evolution of galaxies over cosmic time. More recently, the James Webb Space Telescope, launched in late 2021 and beginning science operations in 2022, has opened up new windows on the early universe with its unprecedented infrared sensitivity. By observing some of the most distant galaxies ever detected, galaxies that formed when the universe was less than 1 billion years old, the James Webb Space Telescope is helping astronomers understand how galaxies formed and evolved in the presence of dark matter, providing new clues about its properties and distribution. Ground-based surveys are also making tremendous contributions. Large-scale projects like the Dark Energy Survey, the Sloan Digital Sky Survey, and the upcoming Vera Rubin Observatory are mapping millions of galaxies across the sky, measuring their distances and properties with remarkable precision. These surveys help cosmologists measure the expansion rate of the universe at different times in cosmic history, map the distribution of dark matter through gravitational lensing, and test different theories about the nature of dark energy. These observations and experiments, combined with increasingly sophisticated theoretical models and powerful computer simulations, will hopefully provide us with a much better understanding of both dark matter and dark energy in the coming years and decades. The mystery is far from solved, but with each observation and experiment, we narrow down the possibilities and come closer to understanding these invisible forces that dominate our universe. The fate of the universe. What happens next? Now that we've taken a deep dive exploring the Big Bang, the relentless expansion of the universe and the mysterious invisible forces of dark matter and dark energy that shape the cosmos, let's shift our focus forward and contemplate the future. What lies ahead for the universe as time continues its inexorable march forward? The universe is constantly evolving, never static, always changing, and understanding its ultimate fate is one of the greatest scientific challenges humanity has ever undertaken. What will happen as cosmic time continues to unfold over billions and trillions of years into an almost incomprehensibly distant future? Will the universe keep expanding forever, growing ever larger and colder, or will it one day reach some kind of end? Could the expansion reverse, leading to a collapse? Could something even stranger happen that we haven't imagined yet? There are several fascinating theories and scenarios about the ultimate fate of the universe, and each one is intimately tied to the fundamental forces and properties of the cosmos that we've been discussing. These include gravity, which tries to pull everything together, dark energy, which pushes space apart, and the overall structure and composition of the universe, including how much matter, dark matter, and dark energy it contains. Let's explore these various possibilities in greater detail, examining different potential futures ranging from the universe's ongoing expansion to its eventual end, whatever form that end might take. Each scenario paints a different picture of the cosmos trillions of years from now, and each raises profound questions about the nature of existence itself. The Big Freeze, an ever colder, darker universe. The most widely accepted theory among cosmologists today about the ultimate future of the universe is known as the Big Freeze, sometimes also called the heat death. In this scenario, which is based on current observations showing that the universe's expansion is accelerating, the cosmos will continue expanding forever at an ever-increasing rate, but this eternal expansion will cause it to grow progressively colder, darker, and more desolate over unimaginably vast stretches of time. The concept of the Big Freeze comes directly from our current understanding of dark energy, that mysterious force that's accelerating the universe's expansion. If dark energy continues to behave as it appears to do now, maintaining its strength or perhaps even growing stronger over time, the expansion will eventually become so rapid that it will fundamentally change the nature of the universe in profound ways. In a Big Freeze scenario, the future unfolds in several stages over timescales that make the current age of the universe seem like the blink of an eye. Stars will gradually burn out. Stars, those brilliant beacons of light and energy that illuminate the cosmos, are powered by nuclear fusion reactions in their cores. Hydrogen atoms are fused together to form helium, releasing tremendous amounts of energy in the process. But this fusion process cannot continue indefinitely because stars have a finite amount of fuel to burn. Eventually, even the longest-lived stars will exhaust their nuclear fuel supplies. As they run out of fuel, stars will fade away and die, leaving behind various stellar remnants depending on their mass. Smaller stars like our Sun will become white dwarfs, slowly cooling embers of formerly glorious stars. More massive stars might end as neutron stars, incredibly dense objects where matter is compressed to extreme densities. The most massive stars will collapse into black holes, regions of space-time where gravity is so strong that not even light can escape. With fewer and fewer new stars being born due to the gradual depletion of the raw materials needed for star formation, primarily hydrogen gas, and with existing stars steadily burning out and dying, the universe will inevitably become an ever darker and colder place. The brilliant starlight that currently fills galaxies will fade like lights going out one by one across a vast cosmic city. Galaxies will drift apart. As the expansion of space accelerates due to dark energy, galaxies will be pushed farther and farther apart from each other. The distances between galaxies will grow at an ever-increasing rate. Eventually, this separation will become so great that galaxies will no longer be able to interact with each other gravitationally or in any other way. They will become isolated island universes, completely alone in an ever-expanding void. Over time, as expansion continues relentlessly, these accelerating velocities will make it impossible for galaxies to collide or merge, processes that currently happen regularly and help shape galactic evolution. Light from distant galaxies will be redshifted so severely by the expansion of space that it will eventually become completely undetectable. Each galaxy will find itself apparently alone in a dark universe, unable to see any other galaxies because their light can no longer reach across the vast gulfs of expanding space. The universe will progressively cool as galaxies and stars fade away and the universe continues to expand. The overall temperature of the cosmos will steadily drop. Space is already incredibly cold, with an average temperature of about 2.7 Kelvin, just a few degrees above absolute zero, but it will become even colder as expansion continues. The cosmic microwave background radiation, that faint glow left over from the Big Bang that currently fills all of space, will be stretched and redshifted by expansion until it becomes so diluted and weak that it's essentially undetectable. Eventually, trillions of years in the future, the universe will become too cold to support any of the processes that create and sustain life as we know it. Chemical reactions will slow to a crawl or stop entirely. Energy will become increasingly spread out and diffuse, unavailable for any useful work. The universe will grow dark and silent, a cold and empty void. A cold, dark, empty universe. The Big Freeze represents a slow, gradual, inexorable decline into an ever colder and darker cosmos. The final state of the universe under this scenario would be a truly desolate place, filled with the dead remnants of stars scattered across impossibly vast distances. There would be burned-out white dwarfs slowly cooling toward absolute zero, isolated neutron stars spinning silently in the darkness, and black holes drifting alone through empty space. There would be no new stars forming because all the gas and dust needed for star formation would have been used up or scattered so thinly by expansion as to be useless. All the processes that once fueled the light, energy, and dynamism of the cosmos would have long since ceased. What remains would be a vast, isolated, increasingly empty space, a cold, dark universe where nothing much happens anymore, and the distance between any two objects is so vast as to be almost meaningless. While the Big Freeze is a scenario that would unfold over an almost incomprehensibly long timescale, far longer than the current age of the universe, we're talking about timescales of 10 to the power of 100 years or more. It represents the ultimate fate suggested by current observations of our universe. It's a fate that's neither dramatic nor sudden, but rather a slow fading away of all the light and energy that makes the universe interesting, leaving behind only darkness, cold, and isolation. The Big Crunch, a cosmic collapse. In fascinating contrast to the slow, cold fade of the Big Freeze, the Big Crunch represents a completely different possibility for the universe's ultimate fate. This scenario would involve a much more dramatic and violent end to the cosmos. The Big Crunch suggests that the universe's expansion will eventually slow down, come to a complete stop, and then reverse direction entirely, leading to a contraction that would eventually compress everything back into a single, infinitely dense point. The Big Crunch scenario is based on the idea that the universe's mass, including all the galaxies, stars, planets, gas, dust, dark matter, and everything else that exists, might be sufficient to eventually overcome dark energy and slow the expansion through gravitational attraction. In this possibility, gravity would eventually win the cosmic tug-of-war against dark energy, pulling everything back together. If the Big Crunch were to happen, the sequence of events would be roughly as follows. Expansion gradually slows. At first, the changes would be subtle and difficult to detect, as gravity from all the matter and dark matter in the universe exerts its attractive pull, acting as a brake on expansion, the rate at which galaxies are moving apart would gradually decrease. This slowing could happen over billions or even trillions of years, making it an incredibly slow process, but eventually, astronomers would notice that distant galaxies are not receding as fast as they used to be. The cosmic expansion that has been ongoing since the Big Bang would lose momentum, like a ball thrown upward gradually slowing as it rises due to Earth's gravity. The expansion wouldn't stop immediately, but it would decelerate more and more as time passed. The universe begins to contract. Once the expansion has slowed enough and finally comes to a complete halt, gravity would begin to pull everything back toward a central point, or more accurately, all points would begin moving toward all other points as space itself contracts. Galaxies, stars, and all matter in the universe would begin to move back toward each other, slowly at first but gradually picking up speed. This would be a reversal of everything that has happened since the Big Bang. Instead of space expanding and galaxies moving apart, space would be contracting and galaxies would be approaching each other. The universe would enter a phase of collapse, with everything falling inward under the influence of gravity. Everything converges toward a singularity. As the universe continues to contract over vast periods of time, it would become progressively more and more dense and hot. Galaxies would begin colliding and merging with each other more frequently. Stars would be packed closer together. Eventually, the spaces between galaxies would shrink to nothing, and all the matter, energy, and space in the universe would be compressed together. As this compression continues, temperatures would rise dramatically. The universe would become hotter and hotter, reversing the cooling that has been happening since the Big Bang. The cosmic microwave background radiation would be blue shifted instead of red shifted, growing more energetic as space contracts. Eventually, it would become so hot that stars would be vaporized, atoms would be broken apart into their constituent particles, and matter would be reduced to a hot, dense plasma. The contraction would continue relentlessly, driven by gravity, until all the matter, energy, space, and time in the entire universe collapsed into a singularity, a point of infinite density and temperature, much like the one that existed at the moment of the Big Bang, but in reverse. At this singularity, the laws of physics as we currently understand them would break down completely. Space and time would cease to function in any meaningful way that we can comprehend. Everything that had ever existed would be crushed together into a single point of infinite density. Could there be a new Big Bang? Some versions of the Big Crunch theory include a fascinating possibility that the collapse of the universe could somehow trigger a new Big Bang, leading to a rebirth of the cosmos. In this scenario, the universe wouldn't truly end with the Big Crunch, but would instead bounce back, beginning a new cycle of expansion. This would create what some cosmologists call a cyclic or oscillating universe, where the cosmos undergoes infinite cycles of expansion and contraction, birth, death, and rebirth, over and over again throughout all of eternity. In this cyclic model, each universe cycle might have different properties, perhaps even different physical laws or constants of nature. Our universe might be just one in an infinite series of universes, each emerging from the collapse of the previous one. It's a mind-bending idea that raises profound philosophical questions about the nature of time, existence, and whether our universe is unique or just one iteration in an eternal cosmic cycle. This idea of a cyclic universe is intriguing and has been explored in various forms by cosmologists and theoretical physicists. However, it remains quite speculative at this point, as we don't yet have enough evidence to support it definitively. There are significant theoretical challenges to overcome, including understanding what would cause the bounce from contraction back to expansion, and whether information from one cycle could somehow carry over to the next. While the Big Crunch is an interesting and dramatic possibility that makes for compelling speculation, it's important to note that current astronomical observations suggest this scenario is less likely than the Big Freeze. The discovery that the universe's expansion is actually accelerating, not slowing down as would be required for a big crunch, makes this scenario seem improbable given our current understanding of dark energy. For a big crunch to occur, something would need to change fundamentally about dark energy. Either it would need to weaken significantly over time, or it would need to somehow reverse its effect, changing from a repulsive force to an attractive one. While we can't completely rule out such changes, since we don't fully understand what dark energy is, current observations give us no reason to expect them. Nevertheless, the Big Crunch remains a theoretically possible fate for the universe, particularly if our understanding of dark energy is incomplete or incorrect. It represents one of several potential endings to the cosmic story, a dramatic finale that would see everything that has ever existed compressed back into a single point, potentially giving birth to a new universe in an eternal cycle of cosmic death and rebirth. The Big Rip, the violent end of the universe. A more dramatic scenario is the Big Rip, in which the universe's expansion accelerates so rapidly that even the fundamental forces of nature are overcome. The Big Rip theory suggests that dark energy, instead of remaining constant, could become stronger over time. As it grows more powerful, it would begin to tear apart everything in the universe, from galaxies to stars to even atoms. Here's steps how the Big Rip could unfold. 1. Accelerating expansion. As dark energy accelerates, galaxies will move further apart at an ever-increasing rate. This could lead to galaxies being ripped apart first, followed by the stars, planets, and any other structures bound together by gravity. 2. Stars, planets, and atoms torn apart. As the expansion speeds up, gravity will no longer be able to hold galaxies together. Then stars, planets, and eventually atoms themselves will be torn apart as space stretches at a rate faster than the forces that keep matter intact. 3. The end of matter. In the final stages of the Big Rip, even subatomic particles could be ripped apart. This would mark the complete disintegration of all matter in the universe, leaving only an expanding void where everything once existed. The Big Rip would likely happen on a timescale of around 22 billion years from now, assuming that dark energy continues to accelerate at its current rate and become stronger over time. It's one of the more dramatic and catastrophic scenarios, suggesting an end of the universe that is violent and destructive. The fate of stars, their life cycles and deaths. Regardless of how the universe ends, the death of stars is a crucial part of its future. Stars are born, live, and die in cycles that shape the evolution of galaxies and the universe itself. Here is a brief overview of what happens to stars. 1. Small stars, like our Sun. Our Sun, for example, will eventually exhaust its hydrogen fuel. When this happens, it will expand into a red giant and shed its outer layers, creating a beautiful planetary nebula. The core of the star will shrink into a white dwarf, a dense, Earth-sized remnant that will gradually cool over billions of years. 2. Massive stars, larger stars live much shorter lives, burning through their fuel at an accelerated rate. These stars will end their lives in a supernova, a massive explosion that scatters the elements created during their lifetimes into space. If the star is massive enough, it may collapse into a black hole, an infinitely dense point with gravity so strong that not even light can escape. The death of stars plays a key role in shaping the future of the universe. Supernovae spread heavy elements throughout space, creating the raw materials for the next generation of stars and planets. These processes also lead to the formation of black holes, which will continue to grow and influence their surroundings, further shaping the structure of the universe. The final moments, a universe of dark matter and black holes. As stars die and galaxies drift apart, the universe will eventually be dominated by dark matter, black holes, and the fading remnants of old stars. In this far-off future, the universe will be an eerie place, filled with isolated black holes, dead stars, and the faint echo of the Big Bang. But even in this dark and distant future, the universe will continue to change, driven by the forces of gravity, dark energy, and quantum mechanics. Whether it ends in a big freeze, big crunch, or big rip, the cosmos will continue to evolve, growing quieter and emptier as it winds down. Perhaps, in a distant future, intelligent beings will look up at the stars, remembering a time when the universe was full of light, energy, and life, and wonder what lies ahead in the final moments of this grand cosmic story. Our place in the universe. As we've journeyed through the origins of the universe, the Big Bang, the formation of galaxies and stars, and the forces of dark matter and dark energy, we've explored the grand narrative of the cosmos. But amidst all this vastness, there's one very personal question we need to ask. What is our place in all of this? In a universe that spans billions of light years and contains trillions of galaxies, it's easy to feel small, insignificant, and lost in the enormity of it all. But as we dig deeper into the fabric of reality, we begin to realize that we are not just observers, we are part of this immense cosmic story. Every atom in our bodies was forged in the hearts of stars that lived long before us. The same elements that make up the air we breathe and the water we drink were created in supernovae, scattered across the universe, and eventually brought together to form the planets, stars, and life we now experience. So, while we may feel tiny in the face of such vastness, we are, in a very real sense, connected to everything in the universe. Let's take a moment to reflect on our place in this grand interconnected story. The elements of life, stardust in the cosmos. You've likely heard it said that we are made of stardust, and there is a profound truth in that statement. The elements that make up our bodies, carbon, oxygen, nitrogen, were all created in the cores of stars, particularly in the explosive deaths of supernovae. These stellar explosions spread heavy elements throughout space, enriching the gas and dust that would eventually form new stars, planets, and in some cases, life. The carbon atoms in your body, the oxygen you breathe, the calcium in your bones, all of these elements have a history that stretches back to the beginning of time through the lives and deaths of stars. These elements were formed billions of years ago in stars that lived, burned, and died long before Earth ever existed. The cycle of birth, life, and death of stars is responsible for enriching the universe with the building blocks of life. In a very real sense, we are part of this grand cosmic cycle. The same processes that formed the stars and galaxies are the processes that formed us. We are intimately connected to the universe, not just as observers, but as participants in this ongoing dance of creation. Our solar system, a cosmic family. Our home, Earth, is a tiny speck in the vast expanse of the universe, but within the context of our solar system, Earth is a special place, a unique haven where life has flourished. Our solar system is a product of the formation of our Sun, which itself was born out of a cloud of gas and dust left behind by older stars. Just like the formation of other stars and planets, the birth of our solar system was part of a much larger process, a process that began long before our Sun took its first breath. Our Sun, like all stars, has a finite lifespan. It will eventually run out of hydrogen, expand into a red giant, and ultimately shed its outer layers, leaving behind a dense core known as a white dwarf. This final phase of our Sun's life will not happen for another 5 billion years, so we have plenty of time to appreciate the warmth and light it provides. Our Earth orbits our Sun at just the right distance to allow life to exist, not too far where water would freeze, and not too close where it would boil away. This perfect balance is what makes Earth a habitable planet, and it's something we tend to take for granted. We live in the Goldilocks zone where conditions are just right for life to thrive. But Earth is not an isolated world. Our planet is part of a larger system, the Milky Way galaxy, which contains billions of stars and possibly billions of planets. The Milky Way is just one of trillions of galaxies in the observable universe, and it's important to remember that our solar system, despite being our home, is just one of many in the cosmic landscape. The Milky Way, our galactic neighborhood. As we step back and look at our place in the universe, we realize that Earth is not just a lone planet in a vast empty space. It exists within the Milky Way galaxy, a sprawling collection of over 100 billion stars, bound together by gravity. The Milky Way is part of a cosmic neighborhood that includes billions of galaxies, each with its own stars, planets, and potential for life. Our solar system resides in one of the Milky Way's spiral arms, about 27,000 light-years from the galactic center. We are located in a relatively quiet, stable region of the galaxy, which has allowed for the development of life on Earth. While there are billions of stars in the Milky Way, many of them are vastly different from our Sun, with their own unique characteristics. The sheer size of our galaxy is hard to comprehend. If we were to travel at the speed of light, it would take over 100,000 years to cross from one end of the Milky Way to the other. And yet, the Milky Way is only one galaxy in a vast universe full of other galaxies, each with its own stars, planets, and potential for life. The Milky Way's size and complexity remind us that Earth is not alone in the cosmos. We are part of a greater cosmic tapestry, one that spans billions of light years, and within that tapestry, our solar system is just one small dot in the grand scheme of things. The search for life. Are we alone? As we consider our place in the universe, the question of life beyond Earth looms large. Are we truly alone, or is life at least in some form common throughout the cosmos? The search for life beyond Earth has been a central question for scientists for centuries, and with the advent of modern astronomy, we are getting closer to finding an answer. The discovery of exoplanets, planets that orbit stars outside our solar system, has opened up exciting possibilities. Some of these exoplanets lie in the habitable zone of their stars, meaning they could potentially support life as we know it. As we peer deeper into the universe, using powerful telescopes and advanced technologies, we are beginning to uncover the potential for other Earth-like planets. And while we have yet to find definitive proof of extraterrestrial life, the sheer number of planets in our galaxy suggests that life may not be unique to Earth. Perhaps there are other worlds where life has evolved in ways we can't yet imagine. The search for life beyond Earth is not just about looking for other civilizations, it's about understanding our place in the universe. If life exists elsewhere, it would imply that the processes that led to life on Earth may be more common than we thought. It would suggest that life in some form may be a natural outcome of the universe's vast and diverse conditions. The universe's future, our connection to time and space. As we ponder our place in the universe, it's important to remember that we are not just part of the past, but part of the ongoing story of the cosmos. The universe is constantly evolving. Stars are born, galaxies collide, and new systems emerge. The events we see today are just the latest chapter in the universe's long history, and the future will bring even more wonders, discoveries, and mysteries to explore. We may be small in comparison to the vast expanse of space, but our ability to understand, explore, and connect with the cosmos sets us apart. Through science, we've managed to unlock some of the deepest mysteries of the universe, its birth, its evolution, and its fate. And as our understanding grows, so too does our sense of wonder and our connection to the universe. In a way, the universe is not just out there, it's in us. Every atom, every element, and every particle in our bodies was once part of a star, and every one of us is part of the same cosmic story. From the Big Bang to the stars to the planets, and to life itself, we are all interconnected in this vast, awe-inspiring cosmos. The human story. our place in the cosmic tapestry. As we conclude this journey through the cosmos, it's important to reflect on what makes us human. We are, in many ways, the universe becoming aware of itself. Through our curiosity, our drive to explore, and our need to understand, we've unlocked the secrets of the cosmos and connected with the stars. We have come a long way from the early days of human civilization, and as we continue to explore space, the universe becomes more and more familiar to us. Though the universe is vast and mysterious, we are not separate from it. We are a part of the same story that began with the Big Bang, and we are writing the next chapter with each new discovery. Our place in the universe may be small in scale, but it is rich with meaning. We are stardust, born from the same processes that formed the stars, and we are connected to the cosmos in ways we are only beginning to understand. Conclusion and final reflection on the Big Bang and beyond. As we reach the end of our journey through the universe, it's time to reflect on everything we've explored and take a moment to appreciate the profound nature of the story we've unraveled together. From the birth of the universe in the Big Bang to the formation of stars, galaxies, and planets, and all the way to the invisible forces that govern our existence, we've touched on some of the deepest and most awe-inspiring concepts that science has to offer. The universe is a place of constant change and evolution. The Big Bang marked the beginning of everything, time, space, and matter, and set into motion the series of events that led to the formation of stars, galaxies, and ultimately, life. It's a story that continues to unfold, with each new discovery bringing us closer to understanding the vastness of existence. The universe, a story of creation and transformation. The Big Bang wasn't just an event that happened billions of years ago. It's still ongoing. The universe continues to expand, and we are still witnessing the unfolding of cosmic history. Every galaxy, every star, and every planet has a story to tell. These stories are not isolated. They are all interconnected, forming the greater tapestry of the universe. The atoms that make up our bodies were forged in the hearts of stars, and the light that once radiated from these stars continues to travel across space, reaching us even today. As we look back at the Big Bang and its aftermath, we realize that the universe is not just a static collection of objects in space. It's a living, breathing entity, full of movement, change, and potential. The birth of stars, the formation of galaxies, and the evolution of planets all contribute to the intricate dance of the cosmos. And just as stars are born and die, so too will the universe continue to evolve in ways we can only begin to understand. Our cosmic journey, from the Big Bang to today. The Big Bang is the starting point of everything we know. It's the moment when the universe began its journey from an infinitesimally small, hot, and dense point into the vast, expanding cosmos we observe today. Every galaxy, every star, every planet, and every living being is the result of this extraordinary event. It's the ultimate origin story, one that connects us all, not just to each other, but to the stars themselves. In the grand timeline of the universe, our lives are but a fleeting moment, and yet, in that brief instant, we are witnesses to an incredible journey of creation. From the first atoms formed after the Big Bang to the rise of stars and galaxies, the creation of life on Earth, and the unfolding future of the universe, we are part of this grand narrative. Looking to the future, what lies ahead for the universe? While we can't know for certain what the future holds, we do know that the universe will continue to evolve, whether it ends in a big freeze, a big crunch, or a big rip. The universe will keep expanding, transforming, and eventually reaching a conclusion. But even as we contemplate the end, it's important to remember that the story of the universe is not just about its end, it's about the journey itself. The future of the universe is intertwined with the fate of everything in it. The stars that continue to shine, the galaxies that are still forming, and the potential for life on other planets, all play a part in this unfolding story. As scientists, astronomers, and explorers continue to study the cosmos, we are gradually unraveling more of its mysteries, gaining a deeper understanding of our place in it. While we may not be able to witness the end of the universe, we are privileged to live in a time when we can ask these profound questions, explore the mysteries of the cosmos, and reflect on the incredible journey that began with the Big Bang. Our connection to the cosmos. One of the most profound aspects of this journey through time and space is the realization that we are not separate from the universe. We are an integral part of it, connected to the stars and the galaxies in ways we are only beginning to understand. The atoms in our bodies, the elements that make up life, were forged in the hearts of stars that lived and died long before our sun was born. This cosmic connection reminds us that we are part of a much larger whole. We are the product of the universe's creative forces, shaped by the same processes that formed the stars and galaxies. The universe is not something out there, it is in us, and we are a part of its ongoing story. This realization invites us to reflect on our place in the cosmos, not as mere observers but as participants in the grand narrative of existence. The mystery of the universe, a never-ending journey. The universe is filled with mystery, mysteries that science has yet to solve, and questions that may never have answers. What existed before the Big Bang? Are we alone in the universe, or is there life elsewhere in the cosmos? What will be the ultimate fate of the universe? These are questions that will continue to drive our curiosity, our exploration, and our search for meaning. As we ponder these questions, we also realize that the universe is full of beauty and wonder. The stars, the galaxies, the nebulae, and the cosmic webs we observe are not just scientific phenomena, they are a source of awe and inspiration. They remind us that we are part of something much larger than ourselves, and they invite us to look beyond our everyday lives and contemplate the vastness of existence. Every time we gaze up at the night sky, we are looking into the past. The light we see today may have traveled across the cosmos for millions, even billions of years, carrying with it the history of the universe. Each twinkling star is a reminder of the vastness of space and the infinite possibilities that exist in the cosmos. A final reflection, embracing our place in the universe. As we come to the end of this journey, we are left with a profound sense of wonder and humility. We are part of something extraordinary, a vast, complex, and beautiful universe that began with the Big Bang and continues to evolve. The Big Bang was not just the beginning of the universe. It was the beginning of everything: time, space, matter, and energy. And from that moment, everything that exists today was born. We may be small in comparison to the cosmos, but we are connected to it in ways that are deeply meaningful. The stars, the galaxies, the planets, and all the life that exists are part of a grand interconnected web. And just as the universe is constantly evolving, so too are we, learning and growing in our understanding of the cosmos. So, the next time you look up at the night sky, remember that you are not just gazing at distant stars, you are gazing at the very heart of the universe, a place where everything began and where everything is still unfolding. We are all stardust, made from the same elements that have existed since the beginning of time, and we are all part of this cosmic journey, however small our place may be. Final words, a peaceful end to our cosmic journey. As we close this journey through the origins and future of the universe, take a deep breath and reflect on the incredible adventure we've shared. The universe is vast, mysterious, and full of wonder, and while we may never know all the answers, the search for understanding is what drives us forward. It connects us to the cosmos, to the stars, to the very fabric of existence itself. So, as you drift off to sleep, remember that you are a part of something much greater than yourself, something infinite, something beautiful, something that began with the Big Bang and continues to unfold in ways we can only begin to imagine. The universe is vast, but it is also full of wonder. Embrace your place within it, and know that you are part of the greatest story ever told.